Okay, I think we're good to start. All right, so good morning, everybody. Welcome to this third and final day of the Statistical Physics of Complex Systems conference. My name is Sebastian Gold, and I'm going to be the chair of this morning's session. And it's a particular pleasure for our first talk to have David Saad join us from Aston University. David, can you hear us?
Yeah.
Wonderful. Yes. We really appreciate that you joined us today, despite some difficulties. We're really glad to have you. And I think you're going to talk about internet routing.
Yeah,
so if you share the screen.
Okay, let me share screen.
Yes, that looks good.
Okay. Okay.
All right, so you have 25 minutes, and then we'll have about 5 minutes for the questions, okay?
Brilliant, thank you. So first of all, I would like to thank the organizers for giving me the opportunity to tell you about our recent research on multi-wavelength internet routing. This work has been done in collaboration with Ije Zhu, who is a postdoc working with me, Jackie Po and Bill Yong from the Education University of Hong Kong. So a brief outline of my talk. I'm going to introduce very broadly the routing problem. I'm going to talk about three different variants of the routing problem called node disjoint, edge disjoint, and wavelength switching routing. I'll explain the specific problems of optical communication, which carries something like 90% of the internet traffic. And we are going to introduce a scalable message passing method for routing in all these three scenarios. I'll show some results and summarize and point to future work. All of this work is on arXiv, as you can see at the bottom of the slide. So what is the problem with routing? So the routing assignment problem is an NP-hard problem because it has interaction of non-local variables. So the non-local variables are the routes themselves, and they are interacting in many different places. Unlike many other hard computational problems like graph coloring, vertex cover, k-sat, and so on, where the interaction is very localized, in this case, the interaction is inherently non-localized. Secondly, if you want to achieve some objective that is non-trivial, there is also non-linear interaction between the routes. For instance, if you want to avoid congestion, you want to spread the routes as much as possible over the network, and this means repulsion between the different routes. If, on the other hand, you want to concentrate on specific routes, you want to attract different routes in order to consolidate the traffic and maybe get rid of some edges that are not of interest. So there have been some works in this area, and I should point to the spanning trees and Steiner trees problems that have been investigated by the Turing group mainly. So clearly the internet is working, so people are using algorithms, but most of these algorithms are actually heuristic. So they use routing tables that monitor the amount of traffic on each one of the edges, and they try to do what is called minimal weighted routing paths. These are shortest path kind of algorithms. In wireless routing, you also do geographic routing. You consider the position of the different transmitters. Other heuristics are to do with measuring queue length and trying to minimize that. There are greedy algorithms. The problem with all of these methods is that they are insensitive to other path choices. That means each one of the routing choices is based on all of the other routes as background. So you may inadvertently route many different routes through the same edges because when you are doing the routing calculation, there is nothing there, and then you overburden specific edges. So it leads to congestion or to low occupancy route. If you have very sparse traffic, you are using the huge infrastructure for no need. There is also a principled algorithm that is being used, which is integer linear programming, but it's non-scalable. So, I mean, people look at 30 nodes, maybe 40 node networks, but that's about it. But you would argue, so what is the problem? The internet is working. Yes, it does, but I don't know why I'm not moving to the next slide. Okay, yeah, but here is the problem. So this graph represents the speed of the internet over years. And the horizontal line points to the percentage of the overall energy production in the world that is going towards running the internet. So while in the 90s, it was 0.1%, and in 2000, it was about 1%, and in 2015 or something like that, it was close to 2%. Now we are close to the 5%. And if we continue with the same rate, by 2040 or so, we will devote all of our energy to running the internet. So obviously, one has to run the internet more efficiently and do whatever one can in order to improve that. So we are part of a consortium with Cambridge and University College London that is aiming at doing exactly that. So I'll briefly introduce the communication model. So we have a graph and comprising n nodes, which we will denote with Roman letters. And then we have m communication requests. So one has to go from one source to a fixed destination. And we have m of those. We can denote sigma nu j equals 1 if communication nu passes through node j, and 0 otherwise. We can do exactly the same thing on edges, but in this particular case, I chose nodes. The traffic on j is simply the sum over all the communications that are going through this particular node. Now, what we can do is try to optimize globally, like minimizing a cost function on a flow, either on nodes or on edges. And we can choose an arbitrary function. It really doesn't matter which one. For simplicity, we chose a polynomial with a power, gamma. Gamma equals 1 simply means shortest path. You are simply counting the number of hops that you have from source to destination. Gamma greater than 1 is a convex function that tries to that penalizes heavily high concentration on specific edges. So if gamma is large, it means that you are trying to more or less spread the load as much as possible. Gamma being smaller than 1, between 0 and 1, is exactly the other way around. It's a concave function. And in this case, you are aggregating traffic in order to reduce the number of active edges. Now, we've had many papers over the years on routing, and this is a partial list on the right. But what I'm going to talk to you today about is a very specific type of routing, which is either node disjoint, edge disjoint, or wavelength switching, which adds another constraint. Now, all of these problems have been solved using a method called message passing, which I'm not going to elaborate too much on, but it is based on the fact that you are passing conditional probabilities to between neighboring nodes until all of these messages that informed your neighbors about your state more or less converge to their asymptotic values, and then you can calculate, infer the values of the variables, and hence also the roots themselves. What I'm going to give as an example is the node disjoint routing. So in node disjoint routing, you have m random communications, and what you insist on is that routes do not cross. So two different routes are not crossing through a single node. So you can describe the system as receivers, senders, and other nodes. So each one of the receivers has resource -1, so it has to be sort of to receive another communication. Senders have +1, and all of the others simply have no resource of themselves. They are not producing or receiving an extra node. So the route is simply passing through edges, and we can denote the flow between edge I and j as +1, between j and I as -1, and otherwise it's the flow is 0. Now, in this particular case, we have a single type of, say, wavelength, and we insist on the fact that it doesn't cross. So the aim is to minimize some global objective, which is a function of the flow, but insist on non-crossing. And there are two constraints. So one constraint is the fact that locally the resource on each node and each message is 0, which is in a way trivial. Because if you're a node and you're receiving a message, you are passing a message and no other message passes through you, then the resource is, overall resource, remaining resource is 0. If you're a source destination, so you either send out a message or receive a message. And the currents are integers, and ij is -iji. So this is work that we've done with Katerina De Bacco some years ago. It's actually very fitting that Katerina is the recipient of the Early Career Researcher Award. So this talk is exactly in the right place. So what happens is that everything is, in this case, is described in terms of probabilities, where you have flows of the different messages on each one of the edges. And because of this specific constraint, the flow can be either 0 or 1. So there is no possibility of accommodating many flows through the same node. Usually, message passing is represented as probabilities, conditional probabilities, but at the zero temperature level, we can map it into a minimization problem on some energies or localized energies. And I mentioned before that we are talking about iteratively updating these variables, which are actually something like a logarithm of a conditional probability. So we are updating them recursively, and this is what we are updating. We are updating the function on the flow plus the this log of conditional probability, something like that, the energy, localized energy of the descendants of this particular node, or the edges that are connected to it, under the constraint. In principle, each one of the messages given a node j can either come into it, leave it, or not pass through it at all. These are the three conditions, the three cases that are described here. So in general, we have to consider 3 to the power of m, because for each message we have 3 possibilities, and we have to consider all 3 to the power of m possibilities in our calculations, which is quite problematic. Luckily, when we are talking about the single wavelength, and if one of the messages is passing through the node, all of the others can't pass through the node. So the state of 3 to the power of m possibilities is reduced to 2m plus 1, because 1 means that you're not going through this node. For each one of the messages m, you can go in either way, from I to j or from j to I, and this is the reason for the simplification of this work, of this calculation. However, when we talk about multi-wavelength, this becomes really problematic, because you have to consider all possible wavelengths, and therefore it becomes exponential in the number of wavelengths, the messages. I should also point, so the first of these two papers, the paper with Katerina as first author is no disjoint. Later on, Katerina and the Turing group followed with another paper on edge disjoint problems. So how is this related to optical communication problems? So in real fibers, in what is called dense wavelength division multiplexing, you have about 156 different wavelengths. And the communication requests are typically order n squared. That means that you want to connect from every node to every node to keep an open channel from every node to every node. So computationally, this becomes really difficult because as a consequence to that, we have an exponential growth in the number of messages, and we have several large-scale variables to consider, and we cannot simply reduce all of them to depend on a single entity. So just to recap about no disjoint, edge disjoint, and wavelength switching. So if we have two wavelengths represented here by the different colors, and we have two messages from J to K and from N to M, we will have to use two different wavelengths in order that they will not both cross the same node I. Similarly, in edge disjoint, we will be able to accommodate the two edges, the two communications from J to K and from N to M, because they just cross the same node, but not the same edge. In wavelength switching, you also can switch your wavelength at I from red to blue and from blue to red, and it offers greater flexibility. So how do we actually do that? So one can consider the setup as a set of Q parallel planes, the number of wavelengths parallel planes. Each one of them has the same topology in terms of the individual nodes. And we assign each one of the communications to eventually one of these planes. But initially, we pass messages from each one of the communications to all of the nodes. If the message mu starts from node I, for instance, so we are connected to node I, and we pass messages both from the communication itself. Both from the communication itself to the nodes, and also from the nodes to one another. Now, I'm not going to explain the equations. You'll be relieved that I'm not going to delve into them. I just wanted to point to show you how these equations look like. So PAIJ is the probability from node I to the edge IJ related to wavelength A, which of the messages is being passed. And this is a very specific and easy one, because one possibility is that the picture on the right, that none of the edges connected to I is actually carrying any message. And the other one is the left-hand side figure saying that a message has been delivered from node M to node I, but bounces back to node N. So it doesn't actually go through this through the edge IJ. Obviously it's more complicated, but if you are interested in the details, you can go to the paper. The other thing that I wanted to point out is what is called the trick of edge disjoint. So in the case of edge disjoint, we can consider the communication between M and N and between K and N, for instance, and map all of this problem into a maximum weighted matching graph, which can be solved. This is a trick that Katerina and the Turing group came up with for edge disjoint, and we are using it as well. Now, the bottom line is that we managed to reduce the computational complexity of this routing task significantly. Remember that M can be very large and Q can be very large, M the number of message requests, Q the number of wavelengths. And specifically, if you look at the case of Q, the same order of the number of vertices, number of wavelengths, the same number of vertices, and number of requests being order n squared, the same message passing is being reduced to order M and Q. Arguably, the lowest number, the lowest order that you can expect, because every node should consider all messages and all wavelengths. And also experimentally, you can see that this is the case on random regular graph, as appears on the right. So what are the measures of interest? The first one is latency. How many hops do you get until, or weighted hops until you get from source to destination? The required number of wavelengths for a given number of requests, the number of wavelengths used per edge, and robustness in general. We examined it both on synthetic networks like random regular graphs, scale-free networks, Erdős-Renyi graphs, and also on the US internet network, which is called CONUS 60, and the UK BT22, 22 edges. These are the main, the backbone of the internet in both cases. Just to make sure that we are doing something sensible, we compared the performance of message passing for edge disjoint, node disjoint, and wavelength switching against linear programming, which can be done for small networks. And so you can see, for instance, for edge disjoint message passing on these two networks, you can see that we get exactly the same numbers for the overall length of edges used and the minimal number of wavelengths to accommodate these messages. So the table generally says it's a sanity check, saying that message passing does work, as well as the non-scalable linear programming. We also looked at the capacity, the number of message requests that we can transmit per number of wavelengths, and we obtain these results for node disjoint, wavelength switching, and edge disjoint. You can see that in general, the more ordered the network is, like random regular graph, which is in blue, the more you can get out of it. When you are looking at CONUS and BT, which are very densely connected relatively, and not they're heterogenic, then you reduce the gain is lower. This is a very interesting result, which is how much we gain by moving in the minimal number of wavelengths needed when we are moving from greedy algorithm, that is represented in blue, to message passing, multiple wavelength message passing, and also in blue, there is wavelength switching. Now, why is it important? First of all, there was a big debate, there still is a big debate in the optical communication community, whether it's worthwhile investing in wavelength switching transceivers. These are the nodes, because they are much more expensive. And the question is, can we gain much by doing that? And at least these figures show that we can get more or less the same performance if we use wavelength switching or normal edge disjoint and node disjoint message passing. The same thing is for edge disjoint, and all of this was done for the CONUS network of 16 nodes and 79 edges. The one thing that in first glance would look as disappointing is the overall average length of the communications. Now, it is not disappointing really, because for simplicity, we did not assign weights for each one of the edges. So on all of these networks, the length is more or less order log n. So you cannot gain much unless you introduce weights on the edges, which can be done easily, but we have not done it just for brevity. Okay. Sorry, this was for node disjoint and this was for edge disjoint, just to clarify. In terms of computational complexity, you can see that there is a polynomial growth in time. This is actual time on a computer. As we increase M, as we increase Q for node disjoint, edge disjoint, and this is in the case of large M, where M is the number of communication requests is order n squared. Moving on, we can consider a more complex objective function. Like, for instance, we would like to get to reduce the congestion by spreading the load over edges, or try to get rid of redundant edges if we take gamma between 0 and 1. And what you can see, this is the overall load per edge, the average load per edge. Sorry, the load per edge, the histogram of the load per edge for node disjoint and for edge disjoint on the right, under the different objective regime. So if gamma is 2, for instance, so let's start with the linear, gamma is 1. This is the orange curve. The green curve shows a peak, a higher peak at 2. So 2 different wavelengths are being occupied on these edges. And there is a decay as x increases. When we look at gamma equals 0.5, you can see that the number of 0 non-traffic bearing edges increases, and there is an increase also on the very right. Delta simply considers, so orange is gamma equals 1, blue is gamma equals 0.5, and green is gamma equals 2. And this is the increase in the more loaded edges, or a reduction in the more loaded edges as we introduce the nonlinear objective. So this is for random regular graph. This is for the conus network. So all is nice and well, but there are a lot of practical considerations that one should take into account when you introduce such an algorithm for a real network. The first one is to introduce weighted edge costs. So each one of the edges has its signal to noise ratio, inherent load, and so on. This is quite easy to do. We've included it also in the work. Legacy and restricted edges. So some of the fibers cannot accommodate all wavelengths. So we have to embed that in the real calculation. There is no problem. We can do that as well. We have done it. Dynamic allocation of new requests. So in reality, you cannot expect to reorganize all of the requests in order to get the best use of the resource. So each time you have, I don't know, in parallel, 100 new requests, and you do the optimization only on these new requests, given the situation as it stands. So we are currently experimenting with our partners in the Transnet network, who are optical communication engineers, on how to do that in the best possible way. Also, we want to reduce the number of wavelengths used and maybe power down some of the equipment. And there are also design problems. Where is the right place to put new edges? So I'll summarize very briefly because I know that I'm running out of time. So we employed methods of statistical physics in order to develop a multi-wavelength routing algorithm and to explore the properties of the algorithm and the networks themselves. And we have derived a scalable optimization algorithm. I hope that I've demonstrated that. And what is very interesting is that we provide a relatively principled tool for comparing between different routing regimes, between different topologies, and so on, like, for instance, the debate about wavelength switching and node disjoint optimization. What next? So we currently are looking at using these methods in real life. And also there are other applications that are very much related to that. So routing in wireless communication, 5G and 6G as relays. So if you want to relay messages through other phones. And the other one is VLSI design. How to have in multiple layers the best possible routing in order to get best performance. Thank you very much.
Thank you very much, David. That was a very interesting talk, very good start to the day. Are there any questions here from the audience? Or online on the chat? Maybe can I start with one question? So it's good to see some message passing equations, but applying these message passing algorithms sort of in the real world is famously hard, right? If you're not in a base optimal setting, that has some challenges. So when you started applying them, so how do you do that?
Okay, first of all, very good question. The challenges usually come in a regime where you have long-range correlations emerging. So in high load, close to replica symmetry breaking, and so on. Most of the optical communication networks are running way below this limit. So even if you have relatively densely connected networks, there is still a lot of capacity in them. So we are not trying to go beyond replica symmetry, which is the assumption of tree-like localized interactions and weak correlation between non-neighboring nodes. So that's how we managed to get away with what we're doing.
Oh, that's very cool. Okay, thank you. Any other questions? I don't see any other questions right now. So maybe let's thank David again then for his talk and for the question. And we'll now move on to the second talk of today's session. Good morning. So our next speaker is going to be Giulio Cimini from Rome University. And he's going to talk to us about the statistical physics of financial networks.
Right. Okay, so thank you for the introduction. Let me, in the meanwhile, I would like to thank the organizer for this invitation. All right, so this talk is about, as you see, statistical physics of financial networks. And what I want to do today is to give you a brief overview of this recent research field with some focus on some recent results. So in order to avoid getting lost, let me go straight to the key points that are not visible. So let me read them. So the first key point is that networks are very powerful tools to model interaction and interconnection within the financial worlds. And in this respect, statistical physics is useful for two things. First thing is that it allows to obtain the topology of this interaction when this information is not known, which is the typical situation. And second, allows you to model the dynamics of propagation of financial shocks over this structure, this network structure. And at the end, I mean, all this together allows you to build precise recipes to do stress tests on financial networks that are actually used by regulators as of today. So so there have been already many talks on networks, so I don't have to explain what a network is. Let me just focus on the specific feature of financial networks in terms of what are the links and what are the nodes. The links are, I mean, there are many kind of links depending on the specific instrument that is exchanged between two financial institutes, banks for brevity. So the simplest interaction that you can have is a loan. You have a bank that lends money to another bank, money, bonds, whatever. But you can have also, I mean, more complex interaction like credit default swaps, which is a specific, particular situation in which you have a bank A, which buys an insurance from bank B over the default of bank C. So you see, this is a three-body interaction. Or you can have indirect interaction arising from the correlation of portfolios, for instance. So many kind of links. In this talk, we will just focus on the simplest situation of direct loans. Besides that, there is also, I mean, a particular feature of financial network is that nodes have an internal structure. The internal structure of nodes is the fact that the nodes are financial institutions, and financial institutions, I mean, have what is called a balance sheet. Balance sheet is this table which is displayed here. You have two columns, the columns of asset, which are the things that have positive values, like loans to other banks, which is these are the interbank loans, but can be, I mean, other things, bonds, stocks, whatever with positive economic value. Then you have the column of liabilities, which are the debts towards the other banks, toward the customers, towards I mean, the rest of the financial system. And the difference between total assets and total liabilities is called equity. This is the net worth of the bank. This must be positive, otherwise the bank has failed. Okay, so this internal structure is what I mean generates the network. In a sense, it will be clear in the next slide, hopefully. The point is, financial network arise because of, I mean, the very reason for which finance exists, which is, I mean, leverage. Leverage is a simple concept, everybody, I mean, here knows, but let me just wrap up here with this nice example. So imagine that we want to buy a house and we have 40,000 euros. So what we do, since the house costs 200,000 euros, we need to borrow money. So we borrow 160, yeah, no, so, yeah, this is the 160,000 euros. So this is our debt. We buy the house, so now we have an asset worth 200,000 euros, and now we have generated a leverage because from our initial capital of 40k, we have now an asset of worth 200k. So we have a leverage of 5. This mechanism is what I mean amplifies gains in financial system, because imagine that now the value of your house increases by 20,000 euros, and so this means that we have a net gain of 20. Yeah, this net gain of 20,000 euros with respect to our initial capital is 50%. So we have a huge gain. So this is the good side of the coin. The bad side of the coin is that if the price goes down, we have multiplied the loss. So this leverage is what generates, this amplification effect in the financial system. But the very fact that in order to have leverage, you need to borrow money. This means that I'm generating a connection within the system. So I'm borrowing money from some other bank, and this allows for the propagation of shocks between me and the bank, because at a certain point, if I fail, the bank will lend me money, will lose the value of this asset. So I will explain this in the following. But so this leverage is a key aspect which then rules all the models of financial contagion in this context. So yeah. Now, few very brief historical facts on financial networks. The literature started around 2000, because I mean before that. Yeah, so there is. Let me just go to this. Before that, the traditional economic, let's say, stream of literature. I mean, we recognize the financial system like a global entity in which the interaction, I mean, were basically neglected. Then, I mean, there was some these first papers are like, yeah, this speech, very famous speech from the director of Bank of England, and then there was some other, yeah, some old papers which started to realize that the interaction are important. And then we had the crisis, the global financial crisis. So this was, I mean, the proof that instability at the local level could trigger, I mean, a crisis at the entire systemic level. So after that, I mean, the lesson that we learned from the crisis was that it was, I mean, mandatory to take into account this interaction to model crisis events. And then, I mean, network-based stress tests have been now are used, I mean, in different financial institutions. Let me describe this plot that I skipped up now. This is a very interesting plot from a paper from 10 years ago by these two economists from Bank of England. In this plot, they used a very simple network model, network Shreni, and they plot the probability of a systemic event as a function of the average connectivity of the network. This was the first evidence that something was, I mean, not trivial in the system. Now, this curve is, I mean, as you see, starts from 0. If you have no connection, there is no possibility of a contagion. Then it starts increasing, but at a certain point, it decreases again. I mean, this going down here is explained by the fact that if you diversify as much as possible, you are basically minimizing the risk of contagion because you have many exposure with low value. Now, the point is that when you see, I mean, when you can measure financial networks, you are most of the time in this region. So taking into account this connection is important. And yeah, so going back to what I want to do, I want to use statistical physics to do two things: reconstruct a network and then model shock propagation. At the end, I will try to show some example of practical application of this framework. So why do we need to reconstruct the network? We need to reconstruct the network because what we have, what is public information that banks gives you is the aggregate balance sheet. So you know what is the total exposure of a bank towards all the other banks in the system, but you don't know the amount of each specific exposure. That, I mean, in network terms, this means that you know the total strength of the nodes, but you don't know the specific weight of the links. So in order to, as it will be clear later, in order to run contagion models, you need to know the network. So the first thing that we have to do is to try to reconstruct this network. And now statistical mechanics is perfect to this task because we have some information that we want to preserve on your system, on our system, which is node-specific exposure, and then we want to do the less biased guess on the structure of the network. So we can use statistical mechanics, in which I just want to say that when you use statistical mechanics of networks, the degree of freedom that you have are the links rather than the states of the nodes. Apart from this, you just do classical ensemble construction. For instance, in an ensemble, you just need to choose appropriate constraints for your system. We don't have now position and velocity, so we need to, have some meaningful assumption for which are the constraints. In our case, it's just the data that we have, so we are basically forced to build the ensemble in this way. Now, the fact that we have node-specific constraints means that we build a canonical ensemble with local constraints. This is, an important point. Now, there are several different ways to do this construction depending on the specific constraint that you impose. We develop different models. Now, well, it turns out that central bankers like the first and more simple of these models for obvious reason, and which I would just want to explain here very briefly. We basically do a two-step inference in which we first try to guess what is the binary topology of the network. And to do this, we use a configuration model, so a canonical model in which we constrain the degrees. But since the degree are not known, we use a fitness ansatz, which is this one, for which the Lagrange multipliers associated to these degrees are taken proportional to the exposure, that is the variable that we know. We can check this assumption is reasonable, I mean, in some very lucky case in which we know the data. And so this at the end, the final outcome of this construction is that we have a connection probability between each pair of nodes, which is just a function of the exposure of the bands that we know. From this, we assign weights according to what is called, I mean, a modified version of the gravity model in economics terms, not in physical terms. There is no distance here, just the product of two masses. So this is a very, I mean, as I said, very simple and effective techniques to generate an interbank networks and was liked very much by practitioners in the field. You can do more interesting stuff. For instance, this is what we call, I mean, granular ensemble. It is simply, I mean, a model in which you consider the links of your network as the particles and the weights of those particles as the energy or the spin or whatever generalized coordinates you want to put on these particles. And then, I mean, you can, thanks to the fact that you can map a weighted network into a lattice gas in an appropriate space. This appropriate space is called triangular graph of the complete graph. It's a bit involving, but in fact it's simple. So you take where is the pointer? Yeah. So you take your original network, and each link of your network corresponds to a node here, and the weight of the link here corresponds to the energy of the particle here. And once you have mapped your system into this space, you can do, I mean, traditional ensemble construction. And for instance, if we impose local constraints, so like the degree and the strength of each node, we end up with a system in which you have a nice connection between local temperature and local chemical potential with your Lagrange multipliers associated to the nodes. I'm not going into details about this. This is, I mean, a slide in which I just showed that this way of modeling a network works very well when you are, I mean, economic system like the World Trade Web and financial systems like the EMID. And it starts, I mean, to fail when you have more, I mean, network like this is, I mean, C elegans neural networks. This is human functional neural networks. I mean, networks that derive from, I mean, possibly more complex generation patterns that what financial networks derive from. All right, so in the last 5 minutes, I want to show you, once you have the network, how you can implement the dynamics of shock diffusion. Now, this plot here is an illustration of the process, and I think it will be enough for now. Imagine that you have this network of 3 banks. Okay, 3 banks are connected because, for instance, this asset of bank 1 corresponds to a liability for bank 2, because bank 1 lent money to bank 2. Okay, so we have this connection between the banks. And now imagine that you have some shocks on first bank. So the value of some external assets goes down, for instance, the price of security owned or whatever. Now, these shocks on the asset becomes a shock on the equity, because I mean now the bank will worth less, will be worth less than before. The problem is that now this reduced equity becomes a reduced asset for bank 3. Bank 3 was the bank that was lending money to bank 1. Why? Because if bank 3 wants to sell the loan, its loan towards bank 1, now this loan will be worth less. And this effectively reduces the equity of the bank in this way. And this process, I mean, is iterative, as you can imagine, and can be written in simple terms. This is the, I mean, famous, well, famous at least in our field, the rank algorithm. which is general enough to include other kind of shock propagation channel. This is what I showed now is called credit shocks, but there are different kind of shock like funding shock, liquidity shock. So and it's possible to extend this framework to account for different kind of shocks. Yeah, so these are just a couple of examples of how debt rank has been used by policymakers. This is the slide from a presentation. This, I think it was from the European Systemic Risk Board of the Central Bank. You see here in this plot, each point is a bank. On the horizontal axis, you have the total size of the bank in terms of total assets. Vertical is the debt rank. So, I mean, the higher, the riskier. And then you see that this relation is not linear. So it's not that the risk is just proportional to the size. The interaction, I mean, amplify effects, especially in this region of the highest banks. These are the too big to fail, in which you have, I mean, very large deviation. So there are big banks that are safe, big banks that are very risky. So this is a quantitative tools to measure, I mean, how risky is a bank. We also did a similar exercise with CCNG, which is Cassa Compensazione e Garanzia, is an institution that it's called Central Counterparty. It's an institution that guarantees the terms of the loans between two financial institutions. So this, I mean, were created basically after the crisis to tame, try to tame systemic risk, but on the other hand, they take risk on their own. So they have a way to measure, to assess what is the level of risk on the system. Let me conclude in the last 3 minutes with some with a kind of question which is which arises from the fact that we often send papers to economic journals, right? So we send the papers to economic journals, and we talk sometimes about equilibrium. Now, it happened many times that there was, I mean, a big misunderstanding with referees, because, I mean, what we call equilibrium is totally different from what is equilibrium according to economists, right? So for us, equilibrium in statistical physics is, we can say that the system is in equilibrium if it's, I mean, well described by the statistical mechanic ensemble built according to some constraints. So if it's a thermal equilibrium, is equilibrium with it, but in general, we can say equilibrium induced by some constraints. Instead, economic equilibrium derives from the fact that you match demand and supply. So they are completely different things. Now, there can be a connection between these two concepts. And this connection derives from the fact that, for instance, in this context of financial network, supply and demand are related to balance sheet variables, because interbank assets is, I mean, the supply, the amount of loans that banks can give to others, and the demand is represented by liabilities. I mean, and so if we take this variable as responsible for economic equilibrium, and if we can say, if we can observe a network which is at economic equilibrium, then we can use statistical mechanics, I mean, the ensemble construction, derive from this constraint to derive all possible configurations which are compatible with the same equilibrium. This is, I mean, in economics is called Barrasian equilibrium, which means that you have an economy in which agents care about only final allocation, but don't care about the specific market configuration. So in this sense, the statistical mechanics way of building networks allows you to have, I mean, to build a network which are compatible with economic equilibrium. And this is the first, I mean, message. Now we can ask, is the systemic risk that we measure on our system compatible with what will be obtained from economic equilibrium? So what we have to do to answer this question is to compare systemic risk on an empirical network with statistical mechanics ensemble for this network. This is what we do in this plot. I mean, very briefly, this is, I mean, on the vertical axis, you have systemic risk. Horizontal axis is a point for each year. This is a comparison between the full lines, which is the rank or real data, and instead the shaded region are the mean and standard deviation of the ensemble derived from the degree and strength constraints. And you see that, I mean, in some years there is compatibility. So this would suggest that the network was at the economic equilibrium at that time. In some years you don't. This is, for instance, 2007, which is the year before the crisis, but mostly 2009 and 2012. What happened in these 2 years? 2009 is the year after the crisis, in which banks were really afraid to end up like Lehman Brothers. So they were, reducing their individual risk. This, caused overall reduction of risk. And the same happened for 2013 in the opposite direction. 2013 is the year when the European Central Bank started to basically lend money for free. And so then banks were more willing to take risks. And so these were two opposite situations in which 2009 risk is lower in real data than in the ensemble. And instead in 2012, risk is higher in real data than in the ensemble, so in the economic equilibrium. Let me go to conclusions. Okay. So I hope that to have showed you very briefly that this network modeling together with statistical physics allows you to build a quantitative tool to assess systemic risk. There are several limitations. The first is data, as it's clear from the need that you need to reconstruct the network. The fact that you assume static behavior of banks, and the fact that you have, only simple interaction. Now, this connects me to the talks of yesterday. So in reality, you have many interactions. So you have multiplex networks, and you have, more than pairwise interactions. So you can have, simplicial complexes also in financial networks. This is, of course, a promising venue for future research. So this is all. Let me advertise some recent reviews, and let me, more importantly, thank all the collaborators that in these years contributed to the fields, and was very enjoyable to work with them. So thank you for your attention.
Yeah, thank you very much. Another very nice talk. Do we have any questions from the audience right now? Edgar.
Hi, thanks for the great talk. I have a question about the canonical ensemble. So you said the canonical ensemble model works very well. Economists like it a lot. I'd like to hear from an intuitive perspective, why do you think it works so well? And also, what's the meaning of temperature in this context?
Yeah, okay. Very nice questions. So the first one, let's say that we are a bit constrained by the constraint that we have to impose, because we just have, we also use the information that we have and build the ensemble. Now, there are different ways to in principle, to start from the matrix marginal, then they build the network. This way is what they found that reproduces better the network. Concerning the temperature, well, it's there is no, you cannot make a parallel between physical temperature. This is, related to the Lagrange multipliers that you use to impose. In our Grand Canonical ensemble is the average weight of the network. That's it. Yeah. And the chemical potential is the density, basically.
Okay, thank you. I have a small question. So when you discuss the differences in what people mean by equilibrium between economics and physics, right? Another way to say in physics that there's an equilibrium, you could say there's no net flows in the system, right?
Sorry, can you say it again? Because of the
that there are no net flows in the system.
Yeah.
Right. Okay. So, and isn't that very close to this idea that demand and supply match? Like, can't you make a connection through that route?
So you are asking, I don't know if I understood correctly. You're asking if in the economic equilibrium you can admit flows, right?
Yeah, basically whether the connection between the two notions of equilibrium is the absence of flows in the system. Net flows.
So the flows will, I mean, in the economic equilibrium, the flows will be responsible for switching the equilibrium point, I think. I mean, I'm not an economist, so but
me neither.
but it should be something like that. So I mean, there are additional, in the economic equilibrium is more complex situation because there are additional variables like the price. So when supply and demand match is the point that determines the price of an asset. Okay, we don't have price in this picture, so I think it's more complex than this. But I don't really cannot say much more about that.
Okay, thank you. I don't see any other immediate questions, so let's thank the speaker again.
Yeah, I have a quick question.
And for the last talk of this morning session, let me start. Wonderful. So for the last talk of this morning's session, we have Ada Altieri from the Université de Paris, and Ada is an expert in spin glasses, and in her talk, she's going to talk about the connections of all the glassy phases in ecosystems. Thank you, Ada.
Okay. So first of all, I would like to thank all the organizers for this invitation. It's a great pleasure for me to be here in Trieste. And today I would like to discuss one of my current projects, which is essentially based on theoretical models in ecosystems, in ecology. And this talk will be based on these two papers. The first one has been published in PRL last June, and the second one is collaboration with Giulio Biroli, and is going to appear in SciPost Physics in a few weeks. So the field of theoretical ecology has gathered momentum in recent years, on one hand reached by an explosion of experimental results and increasingly sophisticated techniques, and on the other hand fostered by crucial questions that still need an answer in theoretical ecology, and range on how does the diversity affect the evolution of the other species? Can we detect cooperative patterns in real ecosystems, and are these patterns ordered, disordered? How does an ecosystem respond to an external perturbation? And is it possible to quantify these functionality responses in a similar way as we do for a physical system? And furthermore, is it possible to detect a multiple equilibrium regime for real ecosystem or more complex, even chaotic dynamics? Well, theoretical frameworks used in the past mostly focused on small number of species on ecosystem formed by small number of species, and mostly employ the theory of dynamical systems. However, when the number of interacting components that can be species, firms in a financial market, in a complex economic network, or neurons in a complex neural network is extremely large, we can take advantage of statistical mechanics tools and statistical mechanics of disorder systems to provide an effective mean-field description and characterize emergent mechanisms and collective behaviors in terms of phase transitions. So for the sake of compactness, I reported just a few works here, starting with Solé, Alonso, and McCain in 2002, going on with Kessler and Schreib. And I want also to mention this work by Tikhonov and Monasson, in which the author proposed a reinterpretation of the well-known MacArthur model, which is a resource competition model, a reinterpretation in high dimension, so with an infinite number of species and an infinite number of resources. And together with Silvio Franz, we rephrase this model as a constraint satisfaction problem. So for people who are familiar with computer science and machine learning, we rephrase this model as a perceptron model in its convex space to highlight that constraint satisfiability can provide a complementary mechanism to self-organizing criticality, edge of chaos, self-organizing stability to explain collective behaviors in large ecosystems. Anyway, today I would like to touch upon another canonical model for disorder ecosystems, that is the Loft-Volterra model with the random interactions. So this model has been recently acknowledged to be a good platform, a good reference model for capturing many different features for various community models that include notably cascade prediction, plum pollinators, resource consumers models, so the MacArthur model that I mentioned just a few seconds ago, by essentially tuning 4 control parameters. So the starting point is the dynamical equation for the relative species abundances, Ni, where I is an index that runs from 1 to S, and S is the total number of species in the pool. So this Langevin equation contains a first self-regulation term that is written as a gradient of a one species potential, that in the case of the Lofka-Volterra model is quadratic in the species abundances, and also depends on this Ki, which are the carrying capacity. So it's a self-regulation term in the sense that if one species, I, experiences overcrowding its immediate environment, it will be pushed back to its own value of the carrying capacity Ki. Then we have this other term, which correspond to the interactive part, and I'm going to better detail in a while. And to add a source of stochasticity, we add this noise, Iti, which is a white Gaussian noise, which has a 0 mean and covariance given by this expression. So it has an amplitude T, is directly proportional to Ni. For this reason, it's called a demographic noise, accounting for death, birth, and other unpredictable events. And as a white noise, is delta correlated in time and delta correlated in the species I and J. And we also introduced this lambda, which is a weak migration parameter, to ensure that all species are present. And at the first level analysis, we assume that this lambda is species independent. So lambda I is equal to lambda for every I. So the main hypothesis, the main assumptions to get an exactly solvable model is to start from a well-mixed community. So we are neglecting any space dependencies in the model. Then we model the noise covariance within the Ito formalism that allow us to preserve the density at finite time. And on top of that, to tackle the staggering complexity of the ecosystem, we assume these alpha ij to be random variables. So these alpha ij are basically extracted from a distribution, which is parameterized by the first 2 moments, mu over S and sigma squared over S. And in this hypothesis, we are basically following Robert May, who was a pioneer in this field, the first study stability and complexity in terms of random matrix theory techniques. So the simplest possible scenario that one can think about is for random symmetric interactions when alpha ij is equal to alpha ji. So in this particular case, the dynamical equation, the Langevin equation that I showed before, admits an invariant probability distribution in terms of an Hamiltonian H, which takes this form. So this is a quadratic term that exactly come into play thanks to this quadratic potential. Then we have the interactive part, and then we have 2 other terms that come into play when we perform the mapping between the dynamical equation that I showed before and the static approach by passing through a Fokker-Planck formalism. So for people who are familiar with disordered system, this can remind you a spin-glass Hamiltonian operator, in particular a soft spin version of, let's say, Sherrington-Kilpatrick model. So to be more definite, to be more precise, this term is a demographic noise that, as I said, can be obtained by just proving the mapping between dynamics and static by passing through a Fokker-Planck approach, and is proportional to the T log n. Then to model the migration parameter, we assume the log of a Heaviside function, meaning that when Ni is greater than lambda, this term does not matter because the log of 1 is 0, and so we don't care about it. But when Ni is smaller than lambda, the Heaviside function is 0, and so the log of 0 is minus infinity, that with a negative sign provides a reflecting world, an arco-repulsive boundary. So this term is properly introduced, is a formal trick, a mathematical trick, to prevent species from reaching very small value, to get extremely close to the boundary. So this model was originally studied without demographic noise and without immigration by Guy Boonin in 2017, and Boonin and collaborators by using the replica method 1 year later. So they basically studied this model without demographic noise and without migration, and they obtained the phase diagram of the model that takes these forms, takes this shape. So sigma is the heterogeneity parameter, I remind you, and mu is the mean interaction. So what they observe in this phase diagram is that when the interactions are small or highly homogeneous, the system is in a single equilibrium phase. Then we can increase the heterogeneity parameter sigma, and the system enters a multiply equilibria phase. However, they did not enter into more detail of the different features of the two phases. And so we can wonder what are the typical features of this equilibria. Are they stable? Are they unstable? And also how many equilibria are there? Are they exponential into the system size? Are they sub-exponential? So to better probe the feature of the two phases and to answer this question, we reintroduce the demographic noise into the model, and we properly study the interplay between these intrinsic source of stochasticity and the immigration parameter. So one possible strategy to do this is to resort to the replica method, which is a well-known technique in disorder system. So I don't want to enter into the mathematical details, but I want just to say that the working strategies is the computation of the free energy in terms of the log of the replicated partition function, and eventually taking the analytical continuation and going to zero, where is the replica index. And so since we are dealing with the disorder quantities, because alpha ij are random variables, we need to introduce two order parameters that are QAB, which is called overlap. So it measures the degree of similarity between two configurations in the replica A and in the replica B. And HA, which in analogy with the physical system will correspond to a sort of magnetization, average magnetization, and here correspond to the average abundance. So thanks to the introduction of these two order parameters, we can basically capture the emerging roughness in the landscape, and we can study in detail the properties of the equilibria in the different phases. So we can, in particular, use improved ansatz that correspond to the replica symmetric ansatz that also David Saad mentioned before, or one-step replica symmetry breaking ansatz that allow us to get information also on the size and the depth of the basin of attraction. So one of the main goals is to better characterize the emergent properties and the emergent collective behaviors in terms of disorder phase transition, and in particular in terms of glassy phases. So starting from this phase diagram that, as I said, was obtained without demographic noise and without immigration, we can pretend now to add another dimension to this problem, to this phase diagram, that will correspond to the amplitude of the demographic noise. And so what happens in this case? Well, what I discovered is that there is no sensitive dependence on the average interaction parameter mu. So we can forget for a while about it. We can fix mu and just focus on this part of the phase diagram. So we can just reproduce a two-dimensional phase diagram for t as a function of sigma. And so this was the resulting phase diagram, where I plot the amplitude of the demographic noise t as a function of the heterogeneity sigma. And so when the demographic noise is sufficiently high to cover random interaction, the system is in a single equilibrium phase. So the landscape is purely convex. Then we can start decreasing the amplitude of the demographic noise t, or increasing the heterogeneity parameter sigma, and the system enters this multiply equilibria phase that, as you can see, is characterized by the emergence of a two-level structure in the distribution of the equilibria. And going deeper and deeper in t, or increasing sigma, the system will cross another instability line in orange and enters another more and more complex phase that is called Gardner. And I'm going to better detail why it's important, especially for glassy systems. So to obtain this phase diagram, I basically look at the stability properties. So I compute the matrix of the second derivative of the free energy with respect to the order parameter of the model, with respect to the overlap, QAB and QCD. And I properly diagonalize this matrix on a suitable subspace, which is called replicon in replica jargon. So this is the final expression for the replicon in the replica symmetric phase that allow us to get information on the stability or the instability of each phase. So when this replicon basically touches zero, it gives information, it gives a signature of an emergent criticality. And so when this replicon touches zero, we are basically approaching this blue line. So we get a quantitative outcomes, quantitative results that allow us to reconstruct the blue line, which is the stability line of the single equilibrium phase. And we can generalize, we can extend this computation to get also the orange line, which is the stability line of the multiple equilibria phase. So another important question that we can ask is how many equilibria are there? How many equilibria are in this multiple equilibria phase? Well, to probe better the features of this intermediate phase between the blue and the orange line, I also focused on the computation of what is called the complexity or configurational entropy. That corresponds to the limit, the thermodynamic limit, so for S going to infinity, of the log of the number of equilibria at the given free energy density, and obviously average over the quenched disorder. So I plot basically the curves of this complexity at different t-value in this intermediate phase, and I discovered that this complexity is strictly positive in this intermediate phase. That if you look at this formula, means that the number of equilibria is actually exponential into the system size, into the number of species. And so this is a first quantitative outcome in this direction, and also extremely timely if we think about stability landscape and ecological resilience concept that have been proposed over the year to explain this apparent emergence of multiple attractors, multiple steady states in the dynamics of real ecosystems. But more interestingly, at very low demographic noise or high heterogeneity, we highlighted another phase that I call it Gardner phase in analogy with glassy system and spin glasses, meaning that each of these locally stable equilibrium becomes now marginally stable. So it splits, it shatters according to a hierarchical and fractal structure. And why is so important for glassy system and spin glasses? Well, you can think about the single equilibrium phase as a sort of liquid phase in which the space of configuration is completely ergodic. So if you look at the dynamics, if you look at the mean square displacement in the single equilibrium phase, the mean square displacement has a ballistic regime followed by a diffusive dynamics at long times. Then you cross this blue line, which is an instability line, as I said, of the ergodic single equilibrium phase, and the system enters a normal glass phase, meaning the dynamics at a long time is no longer diffusive, but as a plateau. And the height of this plateau is basically proportional to the amplitude of vibration of particle inside the cage. If you think about an analogy, if you make an analogy with glassy systems and particle system. And going deeper and deeper in T, the system will cross this other orange line and enters this Gardner phase that, as I said, is characterized by hierarchical and fractal organization of the equilibria. So in this particular case, for the dynamics, we don't have a single plateau, but we should observe a series of plateaus, each of them corresponding to a different time scale, and so a different effective temperature if you think about an analogy with out of equilibrium dynamical systems. And so this is particularly interesting because it was not anticipated, not predicted before in this context. So as I said, with Silvio Franz, we tried to study another model that was the MacArthur model in the high dimensional version, but there we did not find any evidence, any signature of a symmetry breaking effect and of such Gardner phase. So all the results that I presented thus far concern a thermodynamic analysis, a static approach. So what we can claim in terms of the dynamics? Well, we also studied dynamical correlation function, meaning that we look at this dynamical correlator of NT, so of the abundances at time t and the abundance at time t prime, average over all sources of randomness. So the number of species, the number of sample, the initial condition, the random interaction. And so what we highlighted is that in the single equilibrium phase for T greater than T weighting, that it's order 50 is enough in this particular case, the dynamical correlators satisfy a time translational invariant property, meaning that it does not depend separately on two times, T and T prime, but just on a single time scale, T minus T prime. And so as you can see, if you plot the different dynamical correlators at different T primes, all curves collapses to the same value, which is a theoretical predicted value within the replica mythos. So all curves collapse to this Q0 value, which describe the size of the basin of attraction, basically. And so what happens in the multiple equilibria phase? Well, in the multiple equilibria phase, the situation is getting more difficult in the sense that the system never settled down in any of these equilibrium, but start to explore the basin of attraction of the most numerous and marginally stable equilibria, exactly as it happened in mean-field spin glasses, and exactly as was pointed out by Gugliandolo and Curcia in almost 30 years ago in a P-spin model, so in a well-known disordered system models, in which they pointed out an aging dynamics. So the older the system, the longer it takes to decorrelate. And so the model that I presented as far is the Lofke-Volterra model with random interaction that has a tricky part. So it's a purely competitive model. So we cannot describe in this way a cooperative interaction. So at this level, we can wonder what happens if we also plug into the system cooperative interaction. So in the last few, let's say 5-6 minutes, I want to describe this other scenario. So how to model cooperative interaction in large ecosystems? Well, we can use the same, we can assume as starting point the same dynamical equation that I showed before, but we slightly change this one species potential, B of Ni, assuming for this species potential a cubic potential, a cubic shape in the species abundance is Ni. So as you can see, there are 3 fixed points now. One in Ni equals 0, another one in the carrying capacity, exactly as in the Lofke-Volterra model, but there is a new fixed point in M, which is called the Lee threshold. So with this choice of the potential, we manage now to model the so-called Lee effect that describes a positive correlation, a positive feedback mechanism between individuals. So it's a positive correlation between population density and mean individual fitness, as you can see from this plot. So the Lee effect is called strong and is plotted in red when there exists an Lee threshold corresponding to a positive value of this parameter M, and a Lee threshold below which the population goes extinct. And it's called weak, that is shown in orange in this plot, if no threshold, no Lee threshold exists, but thanks to the interaction, there is still an increase in the per capita growth rate when population increases. So this effect can be somehow think about a sort of small population effect, and was observed for the first time by a famous zoologist who was Lee, almost 1 century ago, who first observed that not only competition, but also undercrowding can contribute to limiting the population growth, and can be generated by many different factors that include predator saturation, mate limitation, genetic disease, social dysfunction, and so on. So he first observed that the land isopod a positive effect due to the aggregation of land isopod that, on the other hand, when isolated, tend to desiccation. And so there have been a lot of empirical evidence in many different populations, so reptiles, mammals, aquatic population, but more recently, this effect is gaining an increasing popularity also in engineering biology, in microbial community, and basic epidemiological models. So basic epidemiological models in presence of a strong Lee effect can give rise to surprisingly rich dynamics that range from self-sustained oscillation, chaotic behaviors, and also catastrophic collapses of the endemic equilibria. So the missing point now is try to establish a rigorous and solid theoretical framework to explain this plethora of results. And so what we did is to introduce this cubic potential that nonetheless slightly complicate the analysis, because at variance with the Lofke-Volterra model, now it's associated with 3 fixed points. So as you can see from the first plot, I plot essentially the fixed point of the 2 models. So in the Lofke-Volterra model, we have just 2 fixed points, one in 0, which is always unstable, and another one in the carrying capacity, which is always stable. Here, with the Lee effect, so the curve in orange, the globally asymptotic unstable fixed point becomes a stable fixed point. So now the 2 fixed points are the one in 0 that correspond to the extinction, and the other one corresponding to the carrying capacity Ki. But there is an intermediate fixed point that corresponds to this parameter M, to this Lee threshold, that is unstable. So if you rephrase this picture in terms of a potential of the mean abundance, you can think about the three different situations in this way. So the Loft-Cabothera potential is basically framed within a parabolic potential, so a quadratic potential in the species abundances, whereas the strong Lie effect and the weak Lie effect can be basically described by a two-well or a single-well model. So a strong Lie effect that, as I said, is associated with a positive threshold is associated to a double-well potential, whereas a weak Lie effect that corresponds to negative or zero value of this parameter n is framed by a single-well model. And so if you think about an analogy with the spin glasses, it's like having a nicing model in which you introduce a generalized external field, and thanks to this field, we are basically tilting the position of the two minima. So you are tilting the two potential, and you can switch from this situation to this other situation by passing through a spinodal transition. So given these premises, what we can claim, what we can state in terms of the phase diagram and the responses of this system? Well, we did exactly the same study as for the Loft-Cabothera model, where we plot the amplitude of the demographic noise as a function of the heterogeneity parameter. But again, with respect to the Loft-Cabothera model, we found a completely different situation. So now there is no evidence of an amorphous Gardner-like phase. We can detect just two single phases, in blue for the strong Lie effect and in orange for the weak Lie effect. So just two single phases that correspond to the single equilibrium phase, so to an ergodic and an ergodic configuration space, and the multiple equilibria phase at very low demographic noise or high heterogeneity. And the other important difference is that in terms of the functional response at the variance with the Loft-Cabothera model, now the replicon eigenvalue, so the smallest eigenvalue, which is associated to stability or instability of each phase, does now depend on the species abundances evaluated at the fixed point. So as I said, this multiple equilibria phase is marginal. So we know from the replica method that this phase is marginally stable, in the sense that the Hessian of this free energy has a zero mode, which is this replicon eigenvalue. And as I said, this replicon eigenvalue depends now on the selected point of the dynamics and star. So if we rephrase this condition, this expression for the replicon mode in terms of a condition for the probability distribution evaluated at this effective potential that correspond to the denominator of this expression, we can get an extremely general condition for stability or marginal stability. So repeating, I'm essentially gathering together the two terms at the denominator. I call these two terms the local curvature of an effective potential evaluated at the fixed point and star, and I rephrase this expression in terms of a condition for the probability distribution of this local curvature. And depending on whether this condition is greater than 0 or equal than 0, we can get prediction on the necessary condition for stability or marginal stability in the model. So we use two different approaches, one based on dynamical cavity method and another one based on a Gaussian model of coupled potential. And we look at the lowest typical eigenvalue of this effective potential in such a way that the system can maintain stability when also multi-species excitation are taken into account. And so if we only assume that this probability of the local curvature scale has this local curvature to an exponent alpha, we discovered that we highlighted that essentially these local curvatures should scale in this way, so should have a power law behavior with an exponent greater or equal than 1. So this means that then when alpha is greater than 1, the system is stable when also multi-species excitation are taken into account. And when alpha is equal to 1, there is a marginal stability condition, meaning that logarithmic correction to power law behavior start to emerge. And so this provides somehow a generalization of the argument that was proposed in a different field, so in spin glass model by Anderson, Palmer, and co-workers, in a spin glass model by using a sort of stability energy argument by looking at the number of spin flip that you can apply on your model in such a way to maintain the stability of the system. And so this condition, the condition that we found here, for the probability distribution of this effective potential is more powerful and more general because it allows us also to take into account continuous degree of freedom with respect to a simple Ising model. And so to conclude, I present today two different models, one based on the Lofka-Volterra model with random interaction in which we detect different multiple equilibria phase, both from a thermodynamic analysis and a dynamical approach based on dynamical mean field theory. And also a Gardner phase, which, as I said, is extremely interesting in light of glassy system because it's an amorphous space associated to a hierarchical and fractal structure in the organization of the equilibria. And the important point that I didn't have time to mention is that these models, this Lofka-Volterra model, can be generalized to replicator dynamics, to random replicant models. So if you are interested, there are more details in the paper. And in the second part of the talk, I try also to model this intraspecific cooperative effect that can be particularly beneficial for biological and ecological community, from which I detect completely different transition belonging to different universality classes. And so for the future, it could be interesting also to extend this result to asymmetric interaction and try to introduce a notion of space that can give rise to surprisingly rich dynamics, such as traveling waves of cooperative patterns in this kind of systems. And now, thank you very much for your attention.
Thank you, Ada. There are questions from the audience. Eric.
Thank you for a very contentful talk. There was a lot of material. I have two questions, if I'm allowed to. Okay, so the first one is, there seems to be a flavor, one could think of, multi-person games and finding equilibria in games, in very high dimensional games, which I know is a very, it's a wide field in economics and so on. So my first question is, do you see any relation to this?
Yes, okay. So as I said, this first model, so the Lofka-Volterra model, can be generalized to these random replicant models that have been proved by different authors, also Tobias Galla, and there are also people in the audience like Matteo Marsilio worked on similar connected models, both in economics and also in, let's say, game theory. So there are works in this direction, and the only tricky part is that for the moment, people are considering fully connected models in which there is just a deterministic dynamics. So the next step is try to also model a sort of stochasticity in this model. But for sure, there is a direct connection with game theory, and there are a lot of studies in this direction that try to point it out and to stress the relationship. So in the paper that I mentioned, so the first paper, the PRL, we also did, we added a direct mapping between the two models. So the Lofka-Volterra model and the replicator dynamics that is studied a lot in this kind of other context.
So okay, if I ask one more question? So it's a more general one. I'm not that familiar with this particular models, but there is a related models in population genetics, which I know better. And there you can have some phases where you have effectively a high dimensional dynamics with which satisfies detailed balance, and other phases where they do not satisfy detailed balance. And in population, it's the mutations have to be of a very particular type for it to satisfy detailed balance, but generally they do not. And I guess it's the same thing would be with migration in your model. I'm not sure, but I think so. So my question is more general to game theory and to the possibility that you have dynamics which doesn't satisfy detailed balance. Would this change anything in counting the number of equilibria if you go outside the phase of equilibrium statistical mechanics as a technique?
Okay, so to answer this question, I want to come back to, to this part of the model. So, so this dynamical equation assumes let's say a demographic noise that scales in this way. So it's a multiplicative noise that satisfies detailed balance. Now you can try to model the noise in a different way. So the noise does not scale as Ni, the covariance of the noise in this particular case that you mentioned does not scale as Ni, but the second power of Ni. So it allows us to violate detailed balance and also to have more interesting behaviors like power law behaviors. So in this particular case, when we model this demographic noise in a different way, so still a multiplicative noise, but with a different dependence on Ni, so with the second power of Ni, we should expect power law behavior in the distribution. And so this is particularly interesting also in experiments in planktonic community or microbial population, in which they, several authors have observed a sharp separation, let's say, between many rare species and a few abundant one. And the rare species should have a sort of power law behaviors with an exponent that is that has only small variation across space. So this could be a nice extension of this result to violate explicitly detailed balance and redo the computation.
We have time for maybe one last question. Marco? Maybe while I go over, can you have a look if there's any questions in the chat from the online audience?
In principle, there are, no, I don't see any. Okay.
All right, so thanks for the excellent talk. Concerning this slide, at the beginning you said there is an assumption on the alpha, so there is a reciprocity.
Okay, yes. So this model, so to attain the exact prediction, to attain exact thermodynamic analysis, I assume that the alpha ij are symmetric. So alpha ij is equal to alpha ji. So in this particular case, we can do all the computation with the replica. Cannot go. Okay, with the replica method, because we can associate this dynamical process to a static process. So we have a probability, a quasi-equilibrium-like probability distribution. Otherwise, if the alpha are not symmetric, we can use different approach like dynamical cavity or dynamical mean field theory that have been studied in this case. And so one can wonder what are the prediction in terms of the phase diagram. Well, so for the single equilibrium phase and the multiple equilibria phase, we should expect exactly the same picture because the equilibria here are stable. But when you introduce asymmetric interaction, this Garner phase should be completely wiped out because of the marginal stability property that characterize here the equilibria. And so it was, yeah, it was studied also in related contexts.
Okay, I'm sure there are more questions, but I think we can move the rest of the discussion to the coffee break. Let's first thank Ada again and all the speakers of this morning session. And then I propose that, because I know some of you have connections, that we reconvene at 11 o'clock for the last session of talks.
No? Okay, welcome to the last session of the conference. I remind you that this is the last opportunity to discuss my questions also for the online audience. We will start with two contributed talks in which I remind it's 15 minutes, 15 plus 5. So I leave the stage to Gonzalo.
So thank you. I would like to first thank the organizer for this wonderful opportunity to participate in person in this conference and to allow me to present a talk as well. So my name is Gonzalo Manzano. I'm going to talk about the thermodynamics of gambling demons, which is essentially a new version of Maxwell demon in which feedback control is not allowed anymore, but the demon is allowed to stop the dynamics at convenient stochastic times. So this work has been done in collaboration with people at ICTP, Rosario Fazio and Edgar Roldan, and people in the PICO group at Aalto University in Helsinki, and Diego Subero, Olivier Maillet, and Yuka Pecola. So this is the outline of the talk. I will start with some introduction and motivation of our work. Then I will introduce this concept of this gambling demon and the theoretical results that we obtained. Then I will discuss some experimental tests of the results in a single electron box. And then I will just give you very few points about how this theory can be also extended to the quantum case along quantum trajectories. Okay, so let me start with a brief reminder about the Maxwell demon. Also, Neri Merbat introduced it yesterday. Essentially, Maxwell demon is a thought experiment introduced by Maxwell in 1867 after studying the kinetic theory of gases. And he imagined gas split in two chambers, A and B, which are different temperatures, and which are only communicated by a small trapdoor in the middle, which can be open or closed. So Maxwell imagined a small intelligent being, which was later called a demon, which by looking at the position and velocities of the particles and implementing some control of the trapdoor, is able to sort the molecules so that he may challenge the second law of thermodynamics. In particular, when the demon sees some fast particle in the cold temperature chamber, he may open the trapdoor and let it pass to the other side, so that and the same for the hot for the slow particles in the hot temperature chamber, so that after some time he will get that the cold chamber is colder and the chamber is hotter, in clear contradiction to the second law of thermodynamics. Another related situation was introduced by Leo Szilard in his paper in 1929, which actually did his PhD thesis on Maxwell demon. And in this case is the first model, it's also thought experiment, is the first model of our information engine, in which he imagined a single particle gas in a chamber. But this doesn't work. In a chamber that is operated in a cycle with 4 steps. In the first step, there is a wall that is introduced in the middle. Then in this next step, a measurement is performed to see whether the particle is on the left or on the right, which is done by this small intelligent being or demon. And then an isothermal reversible expansion is implemented in the last step towards the opposite side. So in this cycle, a small amount of work, which is equal to kT log 2, is obtained from the heat coming from the external reservoir, so again in contradiction with the second law of thermodynamics. So although Szilard already pointed that in practice, the measurement step will entail some thermodynamic cost, full exorcism was not available until information theory was fully derived by Klaus Shannon and others. And following this informational exorcism, the violations of the second law of Maxwell-Demons are only apparent violations when one takes into account the informational processing cost. According to the argument put forward by Charles Bennett, if one uses Landauer's erasure principle, one can see that the erasure of the information stored in the demon's memory will entail a minimum amount of work cost of exactly KT log 2, even if it is done reversibly. So there is no free lunch for Maxwell-Demon, and the further development of these ideas has led to a more comprehensive framework for thermodynamics of feedback control, where the information acquired or stored appears explicitly in the non-equilibrium inequalities. And this framework invites us to think about information also as a resource, for instance, is nicely captured in this concept of information reservoirs, as for instance implemented in this nice paper here by Mandel and Jasinski, in which you can operate thermodynamic tasks which will be otherwise impossible in those situations by using a low entropic memory in which you can store information. I will also recall the talks yesterday by Neri and Alexia, and Wednesday by Sarah, which they all provided different examples of this framework of information and feedback control. Much of the theoretical developments were also triggered by very nice experiments that implemented for the first time the thought experiment by Maxwell and Szilard in different platforms. So for instance, in colloidal particles, in optical traps, or in electronic devices, but also in quantum systems like nuclear spins using MR spectrometry techniques, or also in circuit QED systems. Let me just make a remark that Maxwell-Demon has these two basic ingredients. First, the demon gathers information about the microscopic state of the system. And then the demon used this information in order to apply some feedback control over the system, which is just controlling the trapdoor or the piston in the case of Szilard. And the question that we ask in our work is essentially what happens if the second ingredient is not present anymore. So we consider what happens if the demon is not allowed to perform feedback control, but it's only allowed to stop the dynamics. So it's only allowed to do this minimal action of stopping the dynamics at some convenient time. And this is somehow similar to what happens with players in the casino that can decide either to continue the game or quit the game, but they are not able to change the rules of the game. For instance, they are not able to shake the roulette if they don't like the result. So this is essentially the configuration that we consider. We have a system which is in contact with an thermal environment at inverse temperature beta. And we have a fixed protocol, lambda, that is implemented over the system. And so this entails some work. Then the system is monitored. So some degree of freedom X of the system is monitored, and we can see trajectories of the system. And then the daemon can stop eventually the process using what we call a gambling strategy, which is essentially that when a condition is verified for the first time, the daemon stops the dynamics, or otherwise the process continues until the end of the protocol, which is this time tau. So we have this fixed interval of time, and then the daemon can stop either before or when you get to the end of the interval. The time at which the process stops is called stopping time, and it becomes a random variable between 0 and the final time tau. And I denote it with this calligraphic T. So this is analogous to a gambler in a slot machine. Here the daemon has to invest some work that we represent with these silver coins in order to drive a system out of equilibrium, with the hope to recover more work or more free energy than the one that, that the daemon invested. So what happens if the daemon plays this game for a fixed amount of time tau until the end of the protocol? Sometimes the daemon will win, sometimes the daemon will lose, but on average, it is bounded to lose because of the second law of thermodynamics. And the question here is what happens when we don't wait until the final time, but the daemon is allowed to stop the trajectories at some especially convenient times based on the information at hand. And so we ask whether this inequality can be inverted. And of course, those are averages of trajectories of different lengths. And we answered this question in the positive and indeed derive some universal bounds that quantify how much this inequality can be inverted, and also derive some stronger fluctuation theorems of the stopping times. So in order to do that, we use the framework, the standard framework of stochastic thermodynamics with an extra ingredient, which is the use of martingale theory. So what is a martingale process? Martingale process is a especially useful kind of stochastic process, which is defined by this condition there. They were introduced by Paul Levy in 1934. What this condition means is essentially that the best guess for the average of the process M at time tau is a condition on observation of that process until a previous instant of time t. So the best guess is just the last value of the process at the last time the observation was made. And this is a very interesting property that in particular implies the Dub's optional stopping theorem that we will use in order to get our results, which essentially states that the average over trajectories at the stopping times can be related to the average of the process at the beginning of the time. So martingale processes has been studied a lot in mathematics of finance. They are used to model equilibrium markets in which you cannot profit from fluctuations in supply and demand. But they are also been recently seen to be useful in stochastic thermodynamics. And in particular, it has been pointed that the exponential of minus the entropy production is a martingale in non-equilibrium stationary processes, which is this equality here. And I would like to recall that this is stronger than the usual fluctuation theorem for entropy production. And indeed, you can derive the fluctuation theorem by just taking here t equal to 0, so that in the left-hand side, we just have the normal average. And in the right-hand side, we get e to the minus delta, or e to the minus the entropy production at time 0, which is 0, so we will get 1. Yeah, this has been developed in these references here, and also other ones that I had not the space to mention. So this is true for non-equilibrium stationary processes, but it's no longer true in the case of general driving, systems that are generally driving out of equilibrium. So in order to assess this kind of situation, what we had to do is to find another martingale process, which is related to entropy production, but also have an extra term. And this is what allows us to obtain this stopping times work fluctuation relation, in which, as you can see there in the exponential, you have the first term in blue, which is the entropy production in our setup. It's just the work minus the non-equilibrium free energy change during the process, multiplied by the inverse temperature. But we get this extra term delta here that I will comment in a moment. Using this stopping time fluctuation theorem, we can also derive a second law-like inequality, which provides a bound on the entropy production at the stopping times, and which remarkably can be, so the right-hand side of this inequality can be negative, so delta is positive, so that you get something which reminds a lot about the non-equilibrium inequalities with information in the case of feedback control. However, in this case, this delta term has nothing to do with the mutual information. Instead, it's a stochastic version of the Kullbaer-Leibler divergence between the probability density of the process in the forward versus the one in the time reverse process, evaluated at the stopping times. So we call it stochastic distinguishability under time reversal. And in order to better see its meaning, you can look at this picture here down. So here you have the initial density of the process from which the initial state of trajectories are sampled. Then since the fixed driving protocol is applied over time, this probability density changes in time and eventually reaches some rho of x tau. Then in the backward process, the initial state is sampled from this distribution after just changing the sign of the old variables under time reversal. And if you apply the time reverse driving protocol, you will not get the same probability density, but a different one. And this stochastic distinguishability essentially measures the difference, the difference between these two probability densities at the stopping times. So we test our results in a single electron box, which was implemented by the PICO group in Helsinki. So here you can see a scanning electron micrograph of the system. The system is essentially a copper island, which is here depicted in red, which is in contact with the thermal reservoir, which is given by these two terminals. These are aluminum superconducting leads, and they are maintained at a temperature of 0.67 Kelvin. Then we have a gate voltage where we can implement the driving protocol, and a detector that tells us whether there is 1 or 0 XX electrons in the island. So the idea is that, so this is the Hamiltonian of the system. This is a two-level system, an effective two-level system, where you can have either 0 or 1 excess electron in the island. So what we do is to digitalize the current that the detector measures, because it is capacitively coupled to the island. So we can get whether the state is either in 0 or in 1 a long time. And from that, we can obtain the work and the heat during the processes in which we vary this external voltage like a linear ramp. So we move this offset charge of the Hamiltonian following a linear ramp. So what we essentially implement are some strategies that are based on work thresholds. We stop the strategies if you are investing more work than a given threshold WTH, and if not, we wait until the end of the linear ramp. So this is the experimental results that we get. Here you can see the second law inequality in the left and the fluctuation theorems in the right. The dots are the experimental data, and the curves are the numerical simulations. The shade areas are the experimental errors. So you can see that the experimental data follows quite well the simulations despite the errors, and that you can have really a negative W minus delta if for small thresholds. So this in the x-axis, there is the magnitude of the threshold that we implement to stop the trajectories. And you can see that you can really have effective gambling in this situation. In the right part in the right figure, you can see that also in order to recover the fluctuation theorem, you really need to include this delta term inside of the exponential. Otherwise, the fluctuation theorem is no longer fulfilled. So those are some histograms that we also get from the stopping times and from the work probability distribution for different values of the thresholds. So for small thresholds, what you can see is that a lot of trajectories are stopped at the beginning and the middle and in the end of the process. And in that case, the work probability distribution has a lot of negative values, and in particular, the average is negative, so you can extract work in this situation, whether that will be otherwise impossible. But as long as you start to increase the thresholds, all the probability distributions are shifted to the right, so eventually the average becomes higher. And for very large thresholds, what happens is that almost no trajectory is stopped before the end because the threshold is very high. And then you recover the usual probability distribution that you expect for the work with average over the change in the free energy. Okay, so I will, how much time do I have? Okay, so, well, maybe another day I can tell you also about the extension to the quantum case. But let me just go to the main conclusions. So we introduce this gambling demon, which stops the non-equilibrium, or even non-equilibrium thermodynamic process at the stochastic time, according to some stopping strategy that use information about the system. And it does not require feedback control. We think that its applicability should be easier in more situations. We also derive classical and quantum universal fluctuation relations at the stopping times. And we test them, the classical ones, in the single electron box experiment. The results here are for a specific situation with one thermal bath and driving, but in principle, the results can be extended to more general situations, like with several baths and so on. We would like to explore what happens if you apply these kind of ideas in small heat engines, and also whether one can derive optimal strategies in order to stop the dynamics. And it will be also very nice to make this situation autonomous, like an autonomous gambling demon, which is something that we would like to work in the future. So yeah, essentially that's all. Thank you very much. And if you can look at this reference here, and let me also just take the opportunity to point on some recent related work that is also based on martingale theory that we put in the archive yesterday.
Right, there's time for a quick question.
Thank you. Thank you, Gonzalo, for the nice talk. I wonder, since your gambling demo is responsible of the fact that the length of the trajectory is not fixed, I wonder whether one could see it as a sort of fugacity or chemical potential in a grand canonical ensemble, and if so, whether all the things you've done with martingale theory could have done by looking at particular observables, just studying them in the grand canonical ensemble instead of using martingales.
Yeah, I think they can apply also to the grand canonical ensemble because the results are based on essentially on the entropy production, which can be also defined in that case. But instead of just having there maybe the work, well, if you have different reservoirs, for instance, you will get also extra terms from the heat flows and so on. But I mean, you can nevertheless have a stopping time fluctuation theorem like this, but for the entropy production in the process.
Sorry, perhaps what I was asking was not that clear. Could you see your gambling demon as related to a sort of fugacity or chemical potential?
Not to my knowledge.
Okay, thank you.
Okay, let's thank the speaker again. Okay.
Hello. My name is Benjamin Walter. I'm a postdoc here at SISSA. And just before getting started with extreme events of non-Markovian processes, I would like to take the chance and say thank you for the organizers for bringing us together in real life, despite all the obvious obstacles. So today I'm going to talk about extreme events in non-Markovian processes. All of what I'm going to talk about today is contained in this preprint, and which builds on some previous work that came out in PR in January. So this is mostly material that I've developed together with Gunnar Prüßner, my PhD supervisor at Imperial College London, and Guillaume Salbreux, who now is a professor at the University of Geneva. Okay, before getting into the details, I just would like to explore a bit what I mean when I say extreme events. It's not a very trademarked expression. And so for that, I drew a little a sketch. So in red, you can see a one-dimensional continuous stochastic process. And there are a couple of things that you can now ask about the stochastic process that concerns its extreme behaviors, its records that are broken. And so as I just learned in Gambling Demons, you have this question of the first passage time. So for this, what you do is you define a certain barrier at a height x1, and you just wait for the first time tau x naught x1 that your process reaches this critical threshold. Another question that you can ask is the question of the running maximum. So this is the bright green line on top. And so the running maximum at a time t is just the highest value that your process has attained up to a certain time. Equivalently, you can define the minimum. And the difference between the two goes under various names. Sometimes it's referred to as the span, the range, or the volume. And as you can see here, these are all questions that have been addressed pretty much since we have stochastic dynamics. So these are questions that over the last century have always fueled the development of new tools in stochastic dynamics. And actually yesterday evening, I found out that Schrödinger, so you can see that all of these have been published during world wars, but Schrödinger was an artillery officer in the Austrian army during the time, stationed in Gorizia, which is 30 kilometers from here. So what do all of these have in common? So together they really help you to understand the kind of records that are broken by a system. And so what we're interested in is the distribution of these extreme events. So explicitly not only averages, but all moments, the full distribution. And so I'd like to show you a little nice trick. And so this is the object of the visit probability qx of t. So I draw exactly the same trajectory, but now I added a blue shaded area. The blue shaded area is the set of all points that the stochastic process has seen up to point t. So it's the area that's visited by the process. This area itself is, of course, a random variable that is strongly coupled to the trajectory. But now it has a couple of nice features. So suppose you know q of x of t, then you can, for example, take the derivative with respect to time. And so what you do then is you weigh the area that has been visited at t plus dt, but not at t. And so this is exactly the area that's been first visited at t. Yeah, the same you can do by taking the derivative with respect to space. So here you're weighing the area that's been visited at x, but not at x plus dx. So this is minus the weight of the running maximum distribution. And finally, you can integrate out space. And so this gives you the mean span or the mean volume explored at a certain time t. So all I want to do with this slide is to convince you that once you know q of x and t, you really know a lot about the extreme events of your stochastic process. And by the way, q of x of t, the visit probability is, for those of you who are familiar with this, it's the complement of the survival probability. Okay, so let's have a look at a Markovian example of simple Brownian motion, just to get a feeling for this. So simple Brownian motion defined here through its Langevin equation has a visit probability that you can give in closed form. It's 1 minus the error function. And you can convince yourself that with the operations that I mentioned earlier, you get all the correct distributions of first passage time, running max, and mean volume explored. And just here to get a feeling for it, so what q of x of t measures is at t0, you essentially have a delta function. Well, it's not a delta function, it's 1 at the origin and 0 everywhere else. And then as time progresses, the process blooms open, and for t going to infinity, what you get is a constant 1. Okay, so this is the case for a simple Brownian motion, which is probably understood since 1915 or even earlier. And of course, now what we want to do is we want to understand what happens if we go beyond this Markovian regime. So there are many ways to do this. What we did is we induced Markovianity by adding correlated noise. Okay, so this is the same process as before, but now I have this green process y of t, and I just say that y of t is a stationary process with some kind of correlation function. And I want y of t to be of order 1 only for cosmetic purposes, so that I can express the strength of Markovianity with a small dimensionless parameter g. So g now is my coupling parameter and expected to be small. So what does it mean? It means that the random walker experiences kicks at different times s and t, but now these kicks are correlated. So there's memory in the system. So I can repeat the experiment that I did before, and I can see that the black line, which is now a simulation of the curve I showed you earlier, now acquires some corrections. Yeah? So these are small values of g square. I chose an exponential correlator here. There are various reasons to do this, but generally the formalism I'm going to present is not dependent on the particular choice of the correlator. Anyway, the point of this slide is, if you switch on memory, what happens is this shifts, but this shifts only a little. And so this motivates us to assume that there is a kind of perturbative expansion possible. So what do I mean by this? What I mean by this is a little bit of memory is almost the same as no memory, plus a little bit of a correction. So the visit probability is the Markovian result plus g squared times a correction plus g4 times a correction, and so on and so on and so on. And now, first of all, I bury all hope to get a closed form result for qx of t. But what I can at least attempt is I can ask myself, is it possible to compute, for example, this q of 2? Yeah, and so what is the result that we're after? What's the kind of intuition behind this? So if you take this discrepancy here and you rescale by 1 over g squared, what you get is a collapse. So this green line is now the collapsed correction here, and we did this for 2 other values of beta. Beta is the autocorrelation time of the driving noise. And so what you can see here in this plot is basically the non-Markovian corrections are non-trivial in the sense that they're below 0 for short distances, above 0 for long distance. So we can't really expect there to be an effective Markovian description, but there is some hope that we can capture this leading behavior. Okay, and so this is exactly what we did, and we did this using field theory. Now, I don't want to speak too much about field theory. I just want to give you a short overview of the method. So this is a rather technical slide. But the idea here is, as I mentioned at the beginning, we have 2 statistical objects, the random trajectory in red and the visited area in blue. And so what we use is standard field theoretic tools to describe the red trajectory here in red with the field phi. And here you can see this is essentially governed by the associated Fokker-Planck equation. I should say as a footnote, we did this for generic potentials and generic driving noises. And then the second statistical object is the trace. And the trace is an extremely boring subject in the sense that once you have visited a site, it's going to be visited forever. So this is the Fokker-Planck equation of an immortal particle. And now, of course, you have to understand how exactly the red trajectory produces blue area. And this is somewhat more complicated, and this is contained in this interaction. And you can see these references to understand where they're coming from. And then finally, the fourth contribution is this non-Markovian action. So this is the orange part below. And you can see here that, in a sense, the random walker at some time S2 and some time S1 is no longer independent, but they're communicating via the correlator C2 of your driving noise. And so on the right-hand side, for those of you who are familiar with field theory, you can see some diagrams, and what these diagrams represent are exactly these contributions of the action. So I'm happy to discuss all of this afterwards or in person, but yeah, the details are in the manuscript. Okay, so what's the main result? What's the main outcome of this? The main outcome is now that you can use this to ask what's the visit probability in field theoretic language. And without, again, going into much details, the question you're asking your system is, given I start a red trajectory at x0, what's the likelihood that I find a point x1t within the blue area? So these are creation fields. You create a random walker, and then in the quantum mechanic equivalent, you destroy a trace at x1t. And so this average now gives you exactly the probability of having seen x1t. So now if you remember this pathway, there are a couple of things you have to do. You basically expand all the non-Gaussian distributions and evaluate this in a Gaussian average. And if you expand the non-Markovian action, what you get here is just the expansion of an exponential. And you can now identify that the G0 term is exactly the object of the Markovian theory, and all higher orders just naturally pop out of your field theory. So glossing over all the details, what I'm saying here is that field theory is in itself a tool to understand deviations of Gaussian averages. And so in this case, what it does is it gives you a recipe how to generate this queue of n's to arbitrary power. Okay, so I restricted myself to g squared, but there's no reason to do so. You can do g to the 18. And so the main result is basically a recipe, an algorithm. So what comes out is q of n, yeah, so the full distribution to nth order correction. And what you need is a full understanding of the Markovian theory. So the input for this recipe is the transition probability and the return probability of the Markovian process, so for g equal to 0, okay? And the other thing you need to know is the statistics of the driving noise. Now, the nice thing about this is that if you want to understand your correction only to g squared, you only need to know the second moment of your driving noise. And generally, if you want to understand the first nth correction, you need to know the first n moments of your driving noise. So the more you want to know about the correction of your driving noise, the more you need to know about the statistics. But generally, if you're just interested in the leading correction, the correlator is enough. So overall, what this gives us is a systematic, controllable recipe that can generate arbitrary correction terms. And together with the diagrammatics, which I now didn't talk about, you do get quite complicated expressions, but the diagrams explain to you very precisely what is actually happening on the microscopic level. And I didn't talk about all the extensions, so we can do, for example, linear potentials, so we can understand the Ornstein-Uhlenbeck process, and so on. Okay, let's go back to our initial problem. So now this is exactly the same plot I showed in the beginning, but now the solid lines that you can see here are the field theoretic prediction to order g squared. So these are the leading order predictions, and as you can see, they work extremely well in this regime. And this is only to order g squared. So if you want to access sort of higher values of g, then you have to put in some more work. You have to go to higher orders. But what this shows is that you can predict the leading order. And now, just as a reminder, I'm not talking about moments of the first passage times. I'm talking about the full distribution. Yeah. So if you take the respective derivatives, you get the full distribution, and there's no approximation in, let's say, beta, the autocorrelation time, or any kind of diffusion limit. This is the full story. And you can also ask the question for, so now here what I showed you is for fixed value of time versus space, but of course you can also go the other way around. And for that, you fix a distance 1 and you look at time t. Okay, and so this is the same experiment here. I plot the Brownian result. So this is the complement, but this doesn't matter. So this is the Markovian result, and here you can see some discrepancies. If I switch on the driving noise, you can rescale them. And here again, you can see that they nicely coincide with the predictions. Of course, there's some discrepancies here. So part of that is just the numerical noise, but also part of that is then the higher order corrections, g to the 4. Okay, so maybe let me summarize at this point. So what we did is we looked at a particular class of non-Markovian processes that are relevant to active matter or to apparently gambling demons, where you place a particle into a potential and a terminal white noise. And on top of this terminal environment, you now add a little bit of memory, yeah, in form of this self-correlated driving noise. So y of t, again, has to be stationary, has to be, but it doesn't have to be Gaussian, for example. It can be telegraphic noise if you like. And what comes out of this procedure is a recipe where you put in the Markovian transition probabilities and the moments of y of t, and out comes the nth order correction of the visit probability, and as a consequence of a variety of other extreme events. So because it's a field theory, we're not constrained in the things that we want to perturb around. So we could, for example, also look at interactions. So what is the first passage time of n interacting Brownian walkers subject to self-correlated noise? All of this is possible. It's a modular theory, so you can just plug in the interactions you like. And as a more generally summary is, that field theory is a very apt tool to think about memory and stochastic processes. Okay, with that, I would like to close, and I would like to thank you for your attention as well as my co-authors. And again, if you have any curiosities about the technicalities, then please have a look at this preprint, and now I'm very happy to take your questions.
Okay, there's a question here. Okay, very interesting. So the field theory you mentioned is then a 1+1 dimensional field theory, or because in principle you could also have what the particle physicists are doing is 4-dimensional or 11-dimensional, but yours is 1+1 dimensional.
Yes, in fact, there's this other paper where we looked at d-dimensional problems here. So this is the Bordeaux et al. Paper. So you can, of course, also study the area that's visited in a d-dimensional volume. Yeah.
And my second question is, you mentioned the standard diagrammatic expansions that you have in field theory. So how do they look like? What is their interpretation, let's say, in describing the degree of non-Markovianity?
Yes.
There you have some.
Yeah, so maybe, so maybe just very briefly, and then we can maybe discuss later in more detail, but the Markovian theory. So the Markovian here, so if you remember, so red basically is a propagator of the particle, and this we can call a trace. So this is the process where a particle deposits a trace because it's visited a new site, but then you're overcounting and you have to subtract returns. So when the particles come twice to this point already, because that doesn't count, but then you're undercounting, so you have to add the probability of it having had 3 visits, and then you have to, and you overcount and so on. So what you do is you sum all of these diagrams, and so what this says is the probability to be at some point for the first time is the probability to be there minus to have been there twice, plus to have been there thrice, and so on. And so then you can use these Dyson summation tools, and this gives you the Markovian result, which has been known since the 50s. But now your question was, how does the memory enter into this? And so the memory vertex I drew here, yeah, so this means the kick at S2 and the kick at S1 are correlated by the correlation kernel. And so basically you now have the task to combine this Markovian expansion that you can do exactly. You have to decorate them with these loops, which you can't do exactly. But this can happen in 4 fundamentally different ways. And so you have these 4 terms. And then this is a bit of a technical exercise, but once you have understood how these work, then you can summarize them to essentially the main result that I now didn't mention, which is basically you get this formula. This is the formula that comes out if you collect all these 4 different forms. So you have to basically perturbatively correct your transition probability in order to get the new Q function. And here's the formula how to do this. And here you can see that you need the 2-point function of the driving noise. But yeah, there is some diagrammatics behind. I hope this answers.
Okay, there's time for a very brief question.
Thanks for the very interesting talk. You didn't comment on the properties that the memory should have or should not have in order for this to work well into the first order. So of course, G2 should be a small parameter, but what about long range memories?
Yes, yeah, thank you for the great question. So I actually have the correct slide open already. So essentially what C2, this is the Fourier transformed correlator of your noise, has to satisfy is that it has to keep this integral finite. Okay, so this is basically a payoff between the decay properties of your transition probability of the Markovian process and C2. So I haven't found an elegant way to describe the exact properties of this yet, but the clearest answer I can give is C2 has to manage that this remains finite. And this does indeed, for example, if C is integrable, I mean, in the Fourier space, then you're definitely done. So this is, for example, relevant for long-range correlated noise with Hurst parameter above a half. Yeah, thank you.
Right, so let's thank Benjamin.
Hello.
Hi. So next speaker is Kunihiko Kaneko. I remind the last two speakers will be online, and it will be 25 plus 5 of discussion. Okay. Do you hear us?
Yes. Okay. Yeah. Thank you very much for the invitation, and it's quite unfortunate that I cannot come on site. Yeah, I visited Trieste 2 years ago, and yes, but since then, yeah, it's quite difficult to come. Okay, so today I talk about this rather maybe unfamiliar topic for most people, I guess. Okay, so this universal biology in adaptation and evolution. And so universal biology, so maybe that's a kind of new word, but my standpoint in universal biology is as follows. So life system generally consists of diverse components. For example, in a cell, there are many, many different molecule species, not that number, but many, many different kinds of molecules. But still, they can maintain itself, the cell can maintain itself and can continue to produce itself. So maybe here we can put some kind of guiding principle as a kind of micro-macro consistency. So at microscopic level, there are a huge number of different components. So that's a very high dimensional space. And macroscopic level, so for example, cell, that's a unit to sustain and reproduces as a whole. So with this constraint of robustness at a macroscopic level, there may be some kind of low dimensional description for a huge high dimensional microscopic space. So that's quite similar to the spirit of thermodynamics versus statistical physics. But we are not in an equilibrium system, so we need something new. So that's what we aim at universal biology. So the point here is that steady growth state or robustness at a macroscopic level. And the similar idea can be applied from cell to organism or organism to ecosystem. So with this viewpoint, we are working on some kind of cell reproduction, adaptation, and multi-cell organism and evolution. But today, I mainly focus on this. So consistency with molecule level and cell level. And that leads to dimensional reduction to high dimensional phenotypic dynamics for adaptation and evolution. And so that's a response theory. And we can have also fluctuation theory according to fluctuation response relationship that is extended to evolution theory. But I'm not sure, I don't have enough time to talk on this. But anyway, I start from this. So the basic setup for this study is that, so we consider, for example, cell. And in a cell, there are a huge number of components. So for example, in bacteria, there are about 4,000 or 5,000 messenger RNAs or corresponding protein species. So that's a phenotypic space, so very high dimensional. And genotype, that's a rule to determine of this gene expression dynamics or chemical reaction dynamics. then that is governed by DNA sequence. So that gives a rule for dynamics. And so this genotype changes through evolution and according to phenotype changes, and there is some kind of selection. So that's kind of basic standpoint. And I talk about a little bit on the experiment. And in that case, so basically bacteria, E. coli, and taking some kind of many transcription analysis that measures messenger RNA concentrations. And I discuss model for high dimensional chemical reaction dynamics and some theory. So let us start from a rather kind of trivial law. So consider a cell consisting of many components. But for a cell to grow, at a cell division time, almost all components have to be roughly doubled. Otherwise, cell cannot sustain the original state. So it's a kind of stationary growth state. So for example, if you consider I equals 1 to m species, maybe m is 4,000 or something, and ni is the component abundance. Each abundance grows with the exponential. And mu I is the growth rate. But to keep this kind of steady growth, all mu I have to be equal, the growth rate. So, but mu I is generally a function of all other components. So it's, but still it has to satisfy mu1 equals mu2 equals mu3 equals mu 5,000 or something. So there is n-1 conditions. So if you try to change this cell, keeping a kind of steady growth state without differentiating to other cells, keeping this original state and growth and division and growth division process, then there is n-1 conditions. So within this m-dimensional space, this change, keeping steady growth, should be just one dimension. So there is some strong constraint. So we can write up this kind of trivial condition. So consider xi is the concentration of each component. So divided by volume V, and volume growth with exponentially. And this growth rate is mu. So that means each component concentration is diluted with this rate, mu. So that is the equation for this chemical composition concentration. And Fi is including any complicated reactions and many degradation, all these. So Fi is can be a complicated function of all xj. But the steady state means that this should be equal to 0. So that has to satisfy this. Or as a convenience, often it's useful to use log x instead of x. So log concentration. And taking this Fi, xi, Fi, then we can rewrite this equation like this, and then it can be this. And then the steady state condition is just given by this. So here, F1 equals mu, F2 equals mu, and mu is identical for across all components. And of course, mu can change upon the environmental condition. Environmental condition E, so for example, is a stress strength. So by changing E, so this equation has to be satisfied, but mu can change. Now consider from the original state and then put some stress. So originally stress is 0 and put some E's adding some stress. Then assuming that the change is rather small, then we can linearize everything as typical in physics or mathematics. So then we can write down using Jacobi matrix of this Fi, and then also the change of Fi according to the change of strength E. So it's a kind of susceptibility. Then we can write down this delta I delta xi is the change of log concentration, and delta mu is the change in the growth rate. And then we can write down. Then in this linear regime, we can solve this like this. L is the inverse of J. Now, consider two strengths of stresses, E and E prime. Then compare with this. But here, we assume kind of linearization. So that means the changes along this straight line. Then if we take E and E prime, and then this part is common across E and E prime. So from this, we can get this. So that means the change in xj, xi or xj by E and E prime is given by this, but this part is independent of each component. So the change by this each strength for across all components should be proportional. So this is a kind of trivial consequence. But we can check this experimentally. So in this experiment, so we have bacteria E. coli, and they can measure this many different messenger RNA concentration species, messenger RNA species concentration. So that's xi. And then this puts some initial condition and put some stress, for example, put some heat, and then low heat and much stronger heat, or some starvation, a little bit starvation or stronger starvation, or osmotic pressure and strong osmotic pressure, and measure this change log xi from the original to this and original to this, and check this log xi over log xi E prime across all I. I is a different messenger RNA species. So each point here is a different messenger RNA species. So the theory says that this should be located along a single line. Okay, it looks like okay. And the theory also says that this slope should be given by the growth rate change. And so we can measure the growth rate change separately from this experiment in bacteria, how this bacteria grows and divides and grows and divides. And this slope here is obtained from delta mu. So the theory looks okay. And this is for osmotic pressure and starvation. There may be a few points deviated, but here, actually 4,000 points here. So almost all points are along this line. So one strange thing here is that we use linearization, but actually the change or the stress strength here is rather strong. And actually the growth rate of this bacteria is almost 20% from the original if you put some strong stress. But still, this holds. So the first question is that why this linearization works so well? And the second question is that we can check this comparison across a different stress type. For example, osmotic pressure versus starvation, or heat versus starvation. But the theory cannot tell anything because one stress type this direction, other stress types in a different direction. So we cannot compare. And actually, when we divide this gamma I is assumed to be common. And that is okay for the same stress type. But for a different stress type, this can be different. So we cannot divide this. So the theory cannot say anything from that. But still, from the experimental data, we can compare. And okay, it's worse from the previous comparison, but still it looks okay. And actually there are 4,000 points here. And there are more deviation here, but most points here are here. So the mystery here is that there is large linear regime and validity across different environmental conditions. And this is, we cannot say from just steady growth system. Of course, bacteria is not just a steady growth system. It's achieved as a result of evolution. So we can check if this is a result of evolution, but this is difficult from experiments. So we can check by simulation, by taking a toy model of kind of toy cell model with high dimensional chemical reaction dynamics. And for this, so I do not go into details of this model, but this can be discussed in PRL about several times. And so the basic idea is that you have many, many different chemical components. And there are some chemical reaction, Xi, for example, catalyzed by Xj, and Xi is changed to Xk. So for example, in this case, X5 goes to X2, catalyzed by some other X1. And so there are many, many such chemical reactions. And only by this reaction, so many catalysts are produced or exchanged, converted. But then we need some kind of nutrient. So assuming that there are several nutrient species, and XZ goes to some X1 catalyzed by something, and XZ prime catalyzed by to something by X3 or something like that. So we put all these. And the reaction network is assumed to be determined by gene. So that's a genetic gene. Gene determines the reaction network because which enzyme is produced is determined by gene. So that's the rule for this. And so if this reaction works well, then taking nutrients, this cell can grow. And assuming that this cell, the molecule number here is larger than some threshold, it's divided into two, and then repeats this process. And in the division, we make a slight mutation. Mutation means that the reaction network is slightly altered. So for example, put some other path, the reaction path, or delete some other path or something like that. So here, initially, we assume that there are 10 resource chemicals, and of 10, all these 10 chemical resources are identical, so the same concentration. And we did this simulation by using some kind of stochastic reaction network model. So that includes some kind of noise. Okay, and then divides and mutate and divides and mutates. And then after generations, so the growth rate of this cell increases. Okay, we select such higher growth cell, so that's rather natural. So what we can do next is that, can we have this kind of global linear law at this state in comparison to this initial state? And to do that, we put some stress. And stress here is that change resource chemical concentration. So for example, initially I said that all chemical concentration are same for 10 resource chemical, but put some, okay, in some environment stress, this goes to almost zero, and this is increased or something like that. And then we can check if the change of delta Xi by the environmental stress change, just in the same as in the similar to this experiment or as in the theory. So this is the result. So here we plot delta Xj E and delta Xj E prime. It's a different stress condition. That's quite similar to the experiment. And delta Xj is across many, many different chemical components. And I forget to say that in this simulation, we have 1,000 chemical species. So there are 1,000 points here. And what we plot here is that, so after generation 150, so that's the after evolution occurs, then delta Xje and delta Xje prime follows roughly, yeah, single proportion coefficient relationship. But in the initial state, in the initial random network or lower growth state, there is no such structure. And then as the evolution grows or progresses, generation 10 and 150, we can see this linear relationship. And we can see this increase of the correlation through the evolution. Okay, so the initial question that this global proportionality is a result of evolution. So we can verify. But still, why this is so? Now, since we have 1,000 components, it's very difficult to see this 1,000 dimensional space. So we use principal component analysis. So from this 1,000 dimensional space, we have so across many different environmental stresses and how its concentration changes, and PC1, PC2, and PC3. And actually in this case, so this PC3 up to PC3, so the contribution is rather high. So after evolution, and put this original cell, and then put some stress, and put some stress, put some stress. So now each point is a result of different environmental conditions. And after evolution, it follows roughly one-dimensional curve. But in the initial random network, it's just scattered. So that means low-dimensional constraint in this change occurs after evolution. And actually, we also find that if we put some mutation to this original state, that change also follows the same curve. So from these experiment simulation results, we can propose this kind of theoretical hypothesis. Okay, we have this kind of very high dimensional phenotype space, but good state is rather rare. And we have many noise to this system. And if you put some noise, but for this system to be robust, it should come back to the original state in a rather fast. So there is strong stability. So many perturbation goes to this original state. So there is strong attraction to this original good state. But this state has to evolve, or this is a result of evolution. So along the path in the evolution, it should be changed rather easily. Otherwise, evolution is difficult. So that means so across many directions, it changes, this change, perturbation comes back to this. But only along this direction, it can change easily. So that is consistent with this picture or this picture. And assuming this kind of structure, we can rewrite this previous theory. But in this case, one eigenvalue is dominant. So only one mode is very slow, and the other mode is very fast. So from this, we can only consider only one mode. And then from that, and just by simple calculation, we can derive this previous experimental result or theoretical result. And actually, so this kind of evolution result, or this kind of separation, one eigenvalue mode, can be seen directly by measuring the inverse of this eigenvalue across generations. And so this is evolution generations, and only one mode, or 1 over lambda, increases. So one mode is close to 0, and all others, so it's quite well separated. So that's consistent with this theory. So, but recall that phenotypic change due to environmental variation and mutation follows the same one-dimensional curve. So beyond this, across this environmental change, and also across evolutionary change, it follows the same curve. So that means instead of the previous argument, delta xi e and delta xi e prime, but we can consider delta xi e and also delta xi by g. G is a kind of genetic change or mutation, evolutionary change, also follows the same change across many, many components, delta mu, and this is given by just the growth rate change. And we can check this, for example, directly by evolution. And this is the nice experiment by Chikara Furusawa, and put this E. coli into so environmental stress, and then make a mutation by some mutational change over generations. And the growth rate is recovered. And then, so we can measure this transcriptome change, messenger RNA concentration change at each generation. And then we can measure this slope against this environmental change versus mutational evolutionary change. So this is environmental change versus mutational or evolutionary change. And then again, we have this common slope. And actually, there are many scattered points, but again, there are 4,000 points, and most points are along this line. And also, we can check if this slope agrees with the growth rate change, because we can measure the growth rate change from the original state and environmental state and after evolution. And again, so with this growth rate change, and this is the slope from this obtained from here. So there is no fitting parameter. And the theory says that this should follow this line. And over generations, so here, this point here, some generation, and here, some generation, and here, that's some generation. So it works rather well. And also we can check the same thing from this, numerical model, and put some stress here, and then make some mutation evolutionary change again, and check again how this change through this evolutionary change, and then slope change versus growth rate change. Okay, it agrees rather well. So, okay, maybe I have to skip this. So message here is that phenotype change is a high dimension, but their adaptive change are drastically restricted into a low dimensional or one-dimensional space. And phenotypic evolution here is, in some sense, very much restricted into a low dimensional space. And actually, in this experiment, so Chikara Furusawa measured this kind of PC1, PC2, PC3, and all evolutionary courses, and he repeated many, many experiments. But across different experiments, mutation occurs in a different site, but in a phenotypic change, follow the same curve, same low dimensional constraint. So that means phenotypic change, phenotypic evolution is rather deterministic, even though genetic changes can be rather random or stochastic. So that's also a result of this kind of low dimensional reduction. And maybe I don't have time to go into the fluctuation. And actually we can discuss the same thing for the fluctuation. And actually in this case, so each component here change by noise. So each component concentration changes by noise. And so there is variance of each component for concentration variance. And also we can have concentration variance due to this mutation, evolutionary change. And so we can define VGI is that concentration variance due to genetic change. And VIPI is that this isogenic, but due to noise. So the theory says that across all components, this should be proportional. And so, for example, for given mutation rate, this follows the single line. And so that means if one component is very highly variable by noise, it's also variable by mutation. And that means it can be easily evolved. So we can predict, in some sense, phenotypic evolution. And this is consistent with the experiment as shown here. Okay, so I'm sorry, I don't have time. And so we need, of course, further confirmation by experiments of this low-dimensional reduction theory and global proportionality. And so far, theoretically, we checked this in catalytic reaction network model, as I said, but also it's true gene regulation network model. And also, we did some kind of spin glass model. And in this spin glass model, so we consider phenotype of spin configuration, SI, determined by some kind of spin Hamiltonian Jij, SISJ. And here, genotype is given by this Jij. And then we make kind of evolution to increase some kind of fitness. And fitness is, for example, given target spins and align these target spins. And then again, we can consider this evolutionary process and how this target spin change by putting some external field or by putting mutation. And actually, we can see again, across all spins, this is proportional across all spins by evolutionary change and by external field. And actually, that is true only for finite temperature regime. And that is so given by replica symmetric phase. And if replica symmetry breaking occurs, this low dimensional reduction is violated. So we can discuss this kind of low dimensional reduction in terms of spin glass theory in this case. And also we can check of this protein data from this, and that's quite recently published in this case, protein dynamics and protein evolution. And that's again, very highly correlated. But I don't have time to discuss. Okay, maybe I have to skip this. Okay, so today I discussed about low dimensional structure. Low dimensional reduction is formed from a high dimensional phenotypic space as a result of evolutionary robustness. And so we can derive universal law for adaptation and evolutionary relationship. Okay, so that's a result. And actually, one just remark. I moved to Niels Bohr Institute from next year, and so we'll have a new universal biology group at this Niels Bohr Institute, and we'll hire probably 1 or 2 postdocs. So if you are interested, please contact me. Okay, thank you very much. Okay, thank you.
Thank you for the talk. We are a bit out of time, so there's
sorry.
Time for one short question from the audience.
Sorry, my English ability is decreased within this 1 year.
Yeah, there's a question here.
Okay, have you made, or your group or your groups have made any attempt to predict the future of the pandemic using these ideas?
It's
the next mutation.
Yeah, but one maybe interesting point is that, so this kind of, so for example, this is a protein evolution data. And in some sense, if some protein structure is highly changeable by noise, so if it's flexible, then the mutation of this evolutionary change of this protein structure by mutation of each side is also larger. So evolution is higher, evolution speed is higher if it's so the state, phenotypic state can fluctuate more. So it's a kind of quite similar to fluctuation response relationship in statistical physics. And so if it fluctuates more, it's evolved more. But of course, we cannot say anything from this to this COVID thing. But that's a general evolution, consequence. Sorry for this.
Okay, so the last speaker of the conference is Celia Anteneondo, and we hope she's online.
Oh, sorry.
Yes, I'm here. Wait to share the screen. Okay.
Yeah, sorry. Yeah.
Okay, can you hear me?
Yes.
Okay, so hello, everybody. Good morning. I'm in Rio de Janeiro. Here is 7 in the morning yet. So I want to thank the organizers for the opportunity to talk here. So I will present some recent results that we obtained in a collaboration with David Kessler, Eli Berkay from Maryland University, and also Luciano De Faveri, who actually is currently at PUCI, but he's moving to Maryland as a postdoc. I will start with this visual abstract to transmit you the main ideas. Here, what we consider are particles in a thermal environment, that is Brownian particles, and they are subject to potential of the kind plotted here, where there is some region where the potential is confining locally, but at long distances it is flat. What we observe for this kind of system, when we look at the evolution, time evolution of some quantity, in this case is the square displacement, but maybe a thermodynamical quantity too. What we see is that there is a time interval where we see a plateau. The quantity remains in average almost constant, and the length of this interval may be very long, depending on the temperature relative to the depth of the well. So this is what we see under certain conditions, and the idea is to define the conditions where such kind of states that we call quasi-equilibrium states appear, and also to predict the values of these states. So if we pick the usual partition function, of course it is divergent due to the flatness of the potential. However, what I will show that we can still use this partition function after a proper regularization. Well, this is the central ideas that I will now transmit in more detail. So concerning non-confinement, these kind of potentials that are flat at long distance, of course, are very common in nature, from Columbian or gravitational or intermolecular interactions. Here we are thinking more in some kind of surface or membrane in an environment where particles can diffuse and feel attracted by this surface potential with a certain law that decays with distance of the kind of these plots here. And what we consider is Langevin dynamics for the simplest case of overdamped dynamics, but this is not necessary. Also, what I will show is for the one-dimensional case, this is also valid in more dimensions. And the kind of force we will consider here comes from a potential that has this shape. Also, for simplicity, we are considering a shape that is symmetric, has a certain characteristic length, and there is an exponent here that allows to control the decay to zero. So this is what we consider, but in the presentation, we have also looked at what happens with other kinds of potentials that are less simple than this one. Also, potential like generalized Lennard-Jones and other kinds. But I will focus on this kind. So actually, we treated the problem with a Fokker-Planck approach corresponding to the Langemann equation I have already shown. In this equation, we can scale some variables so that we reduce the Fokker-Planck equation to this form where actually there is a main parameter, a control parameter, that is this scaled temperature with respect to the depth of the well. And besides that, we have the parameter that controls the decay at long distances. But this is the main parameter. Most plots I will show will be related to this one, if I forget to tell. So when we solve numerically the Fokker-Planck equation and compute quantities, for instance, the mean square displacement, we see that this is the scaled temperature. For high temperature, of course, the potential is irrelevant, and we see a behavior of free particles. But when we decrease the temperature, we start seeing the appearance, the emergence of this kind of flat region. Of course, at later times, the particles will escape the well, and we will see again free diffusion. But this is the kind of state that we call quasi-equilibrium in this problem, and that I will try to describe. So if we look for a stationary solution, of course, we will obtain a Boltzmann factor, but as I said before, it will be non-normalizable. The thing is to regularize this quantity so that we can calculate average through a recipe. Just to understand what happens in this problem, if we are considering an initial concentration around the origin, and at short times, what we will have is that this packet will expand, filling the bottom of the well, particles will diffuse in the bottom of the well. At long times, where there is a probability of the particles escaping, we will again see free diffusion. What we are interested in is in the intermediate times, intermediate between these extreme situations. And in these intermediate times, what we see is that the central part of the probability density function remains almost constant. This is after some transient time where the particles diffused and occupied the well. And this is what we see. Most of the probability is concentrated in this region. And we see these tails. Here is in more detail the cutoff, the tail of the distribution, here divided by the Boltzmann factor. And this tail diffuses, but here the probability of course, at very long times, this will be a diversion, but at short times, we see that this cutoff will be effective so that we can integrate this probability. So I will try to summarize how to perform the regularization procedure for these intermediate time scales. I will forget the initial and long times for which free diffusion is observed. Will be trying to describe this central region for intermediate time scales. So what we see here is that for position around the central part of the well, we have this something proportional to this Boltzmann factor, and we can approximate the tails by a complementary F function. Since here we have diffusion, but not starting from the delta, but from almost uniform initial distribution. And we can match this solution for short and long distances. This can be done simply by the product, since this will be almost, will tend to 1 for long distances. This will be approximately 1 for short distance. So we can make this product and match both behavior for near the well and far away. We have also solved the problem through eigenfunction expansion, but I will refer to this form that is more intuitive. So what we do to find this normalization constant, to integrate, the procedure is basically to split the integrals, rearrange terms. Here we can, when we integrate, we split into regions around this L is some crossover point between the two regimes, and that we can determine. But here we'll see that it is independent. If you assume that this point exists, we can, when we perform the integration, since each factor is almost 1 in one of the regions, then we will have this summation of 2 integrals. Then we can complete this integration from 0 to infinity, and this is essentially 1 in the small x region. So this 1 we transfer to the first integral and split it into parts. So we decompose the whole area in regions that have well-defined characteristics. This term will be negligible. This term we can integrate exactly, and it will scale order square t. So it can be very large at long times. And this first is the term that is time independent and is dominant at intermediate scales. So here, making a relation between these 2 terms, we can extract the time scale that defines the exit from the plateau. But for times such that this term is much larger than this one, then we can approximate the normalization constant. But this function that resembles a partition function, but it was regularized by this term, similar to what is done in the virial expansion. So what we have here is the normalization factor. Now we can do this same procedure for the other integral, for instance, integral in the numerator here. We can also rearrange and split terms, and we obtain a similar factor, a similar regularization, but this will correspond to, this is the exponent of the k of the potential. This will be valid for a rapid decay. This I didn't comment it, but this is valid for a decay that is 1 over x. So this regularization actually will depend on the potential, how fast it decays, and also on the observable. What we are actually doing is to introduce some correction that will avoid the divergence. But we see that the result is very good compared to the numerical solution. These lines are the prediction. This is just the inflection point. These lines are a comparison with the exact numerical solution. actually, as I said, if it will depend the general procedure to regularize the partition function will depend on the potential and on the observable. So in general, what we will have to do is to subtract not only one, but more terms in the expansion of this exponential. As a concrete example, here I present the case where the decay of the potential is 1/x, and I'm trying to calculate again the mean square displacement. So you see that for the normalization factor, I need in this case to subtract one additional term. In the case of the average of x squared, I will need to subtract more terms to compensate the weight of the tails for this kind of observable. I will not enter in detail in these plots. Here, this is the same plot, and here is for 1/x, where I showed that the prediction works very well. Actually, what one is, the approximation one is making with this regularization can be seen writing the approximated the potential as with this form that is compared here in the graph. This is the solid line is the true potential, and this dashed line is the approximation that we are doing in comparison here with the harmonic approximation. So you see that in the central part, it works well as an approximation, even in a case that is rather a limit, in the sense that this is expected to work better for lower relative temperatures. And here is again the comparison. The dashed lines are our approximation, and the dotted ones are the harmonic. You see that there is a discrepancy. So we managed to obtain a more precise approximation than simply harmonic. It's also interesting that we recovered several relations of the equilibrium conditions for this kind of states. And we also compared other observables, obtaining also good prediction. I wanted to comment also on another perspective, another way to see the problem that can give insight, that is to consider our original potential, but not to wallet well. So that in this case, the evolution will lead to a true equilibrium situation that we can integrate. And so we can calculate this probability and obtain now the averages as a function of L. You see that we obtain the plots that resemble the plots that we obtained as a function of time. Also, the approximation will be better for lower values of the relative temperature. Here is a comparison of the result for the time evolution and the result using this approximation. Obviously, the prediction will have the same values. The values will be the same. It is as if putting the wall fast from the origin, we were letting the particles diffuse far away. So in this case, we can make to obtain the limit L to infinity. We can also split the integrals and determine the contribution of each term. I will not enter in that detail now. So what I wanted to emphasize here is we know some information about the time evolution. The prediction of values can be performed in the same way. The expressions, the regularization is the same. And here, what we can use to characterize the states is a log inflection point. So in the case of the bounded domain, where we can calculate a true equilibrium state, we can obtain analytically the inflection point. We then can know when these states can exist or not. Here is the calculation. These are the functions that, when equal to 0, give me the solutions that provide the inflection point. You see that if the temperature is too high, there will not be an inflection point. So we can determine which is the minimal requirement to observe this kind of states. And we can then define the averages as the average calculated. We have the average as a function of L, but we can estimate the inflection point and calculate the average in that point that will provide the quasi-equilibrium value. So here is a comparison of the low inflection point obtained by the L perspective and the time perspective, the circles. This is the end where there are no more inflection points. They do not coincide, but in the region where they are expected to give good results, that is when the relative temperature is sufficiently low, there is a coincidence between these results and those obtained here for the exact calculation from the integration, numerical integration of the equation. This, for comparison, is the harmonic approximation. I just wanted to comment that we performed calculations using eigenfunction expansions for this intermediate region where the quasi-equilibrium appears. I will not show the calculation, but just to recall that when I tried to explain how we apply the regularization procedure, I used this approximation, and in fact, through the eigenfunction expansion, we can arrive to expressions that justify that choice. Actually, there is a shift in the error function, but this matching of the two regions work very well. This one will describe the initial vision, the other the tails, and the crossover is very thin. So these two solutions match almost perfectly. So I compensated the time that Professor Kaneko exceeded. I just wanted to remark that we have find this kind of quasi-stationary state that we call quasi-equilibrium, actually not normalizable quasi-equilibrium. And we found a procedure that allows to regularize the partition function so that we have a recipe to calculate the average in the non-normalizable quasi-equilibrium states. Well, this is essentially what I wanted to transmit to you.
Okay, thank you very much for the great talk. It's time for questions. Right, the audience is maybe a bit tired of all this conference, but I have a short question about the method. So mainly the method is based on an integral, and you break the integral into parts, and you have this error function approximation. So my question is, you showed for which type of potentials this technique works. Could you say something on which type of potentials this technique is not suitable, or you have to modify this error function by another type of function such that all the regularization changes?
No, look, the error function approximation is not actually necessary to find the regularized states. Let me see here. When we split the integral, we have this, that is R function. But if we use it actually another effective cutoff, this will work, because what we are keeping is just this first term that is not time dependent, and the cutoff will be important to determine this this crossover point. But this point is not appearing here. We should assume that it exists, but if it exists, then we can determine this integral, which is time independent. The term that is time dependent, what will give us is the characteristic time of exit of the plateau, for instance. But here is heuristic, but we obtained the exact solution through the eigenfunction expansion.
Okay, thank you. Another question?
Well, another thing, what may happen is that the quasi-equilibrium states do not exist dependent on the potential. For instance, for a log potential, we don't have this kind of states.
I see. Thanks. Other questions? Okay, if there are no more questions, let's thank all the speakers of the session. I will briefly call Sebastian to the stage, so we will conclude the conference with some remarks.
Do I get to?
Okay, so we want to thank all of you for being here. It's been, it's been a big challenge. This conference is the first. It's been the first ever hybrid conference in Trieste, and for many of us, and I think for all of us, and it's been really a lot of work from the side of, we have to do an online conference and an in-person conference, and lots of changes in the last minute. So if any of you is going to organize one of these, keep in mind that things change until the last minute. But this has been possible thanks to many people, both from SISSA and from ICTP. So we want to thank all these people. First of all, scientific people, which are the APS Commission, Matteo Marsili, Andrea Gambassi, Stefano Ruffo, also the video team, which has kindly arranged all this. For them. Because this room was not ready 10 days ago and all the protocols are new, so you can imagine. And next, also the SISSA people. This should be Sara and Emanuele, who took care of all the bookings, hotel bookings, and all the arrangements for you to be here. I think they also deserve a big clap. And last but not least, the ICTS team, which is everyone who made all these Zoom sessions possible, and they did all the technical stuff. So also a big clap for them. And finally, the EPS, which kindly was extremely motivated to come here. We were for a long time thinking, is this going to happen? And this was thanks to the momentum and the motivation of mainly Christian, I must say, and also the commission from EPS. So thanks a lot also for you.
And certainly, in addition to these people, I want to thank Edgar and Sebastian, who did a marvelous job, really, and really a lot of work, and were always available for email answers. So thank you too, in particular, in addition to the people that you mentioned already. Thank you very much.
So this is it. Lunch is waiting, and we've been a bit late today, so have a safe trip back home.